For as long as humans have gazed up at the night sky, the shimmering stars have held a profound allure. Their distant light, wandering through the vast cosmic sea, evokes a deep sense of wonder and a persistent curiosity about what lies beyond the confines of our own pale blue dot. Among the myriad questions this curiosity births, none perhaps resonates more compellingly than the search for other worlds, planets beyond our solar system, and more intriguingly, those worlds that might harbor vast oceans. This fascination is not simply rooted in scientific inquiry. It's a narrative that entwines our thirst for knowledge with the profound human yearning to find company in the cosmos, to understand our origins, and to imagine countless other possibilities for life and environment beyond Earth. Long before we possessed telescopes capable of peering into the depths of space, our ancestors speculated about other worlds. Ancient civilizations, rich with mythology and storytelling, often portrayed the heavens as inhabited by gods and spirits, or even by realms mirroring our own. These stories formed an early framework for humanity's cosmic longing, an imaginative precursor to the scientific pursuits that would emerge millennia later. As our technological capabilities advanced, so too did our ability to verify that our solar system was but a fraction of the universe's grand tapestry. The discovery of planets orbiting other stars, or exoplanets, has transformed speculative thought into rigorous science, expanding our horizons in ways once limited to science fiction. Among the vast diversity of exoplanets discovered, those that may resemble ocean worlds ignite particular excitement. Earth's oceans have long been recognized as cradles for life. They regulate climate, support complex ecosystems, and serve as critical agents in shaping our planet's geology and atmosphere. The possibility that distant planets might have similar aqueous expanses invites thrilling questions. Could these alien oceans foster life? How do the properties of these alien waters differ under the extremes of pressure and temperature found elsewhere? What might the skies and surfaces of these worlds look like? And how might they challenge our understanding of planetary science? The concept of ocean planets, or water worlds, is a relatively youthful branch of exoplanetary science that has captivated astronomers, astrobiologists, and space enthusiasts alike. These worlds are envisaged as planets where water dominates the composition, enveloping the surface entirely and possibly harboring thick global oceans dozens or hundreds of kilometers deep. Unlike our Earth, where oceans cover a significant but not overwhelming portion of the surface, these planets could be almost entirely aquatic, with atmospheres laden with water vapor, clouds of exotic composition, and geological dynamics vastly different from anything we experience here. What deepens our fascination is the fact that finding and studying such planets is not merely a distant dream. Over the last 2 decades, the advent of sophisticated space-based observatories and ground telescopes has enabled scientists to identify thousands of exoplanets, some of which fall within the size and mass ranges consistent with ocean worlds. Among these mysterious bodies, a select few have emerged as prime candidates for detailed study, promising to reveal the complex interplay between water, atmospheres, and planetary interiors. Humanity's interest in these alien oceans is intertwined with our quest to understand habitability and the potential for life beyond Earth. While every planet we discover brings new clues, each ocean planet offers a unique laboratory where conditions might drastically differ from terrestrial standards. High-pressure ice layers beneath infinite oceans, superheated atmospheres, or alien chemistries all paint worlds alien in the most poetic sense. Yet they beckon as possible abodes for life in forms yet unimagined. Moreover, the study of ocean planets challenges and expands our definitions of planetology. Where once planets were simply rocky or gas giants, We now consider a spectrum of possibilities that can redefine planetary classification. Ocean planets remind us that the universe is wildly creative and often defies our terrestrial preconceptions, urging scientists to develop new models, instruments, and missions to better understand their mysteries. Beyond pure science, these worlds inspire art, literature, and the collective imagination. Their all-encompassing waters, alien skies, and potentially unique biologies ignite narratives that explore the profound relationship between life, environment, and destiny. They compel us to ask not only scientific questions, but philosophical ones. What does life look like in alien oceans? How might sentient beings, if they exist, perceive their world? And ultimately, what does the existence of ocean planets tell us about our own place in the cosmos? In setting the stage for our journey into the specific case of Gliese 1214b, we immerse ourselves in this rich tapestry of human curiosity and scientific discovery. Gliese 1214b is one of the most studied ocean planet candidates, an alien world that embodies many of these compelling questions and mysteries. Its discovery marked a milestone in exoplanet exploration, opening a window into the possibility that water-rich planets may not be rare, but perhaps a widespread and diverse class of worlds in our galaxy. As we embark on this exploration, it is worth pausing to reflect on the broader significance of our pursuit. The search for alien oceans is not simply about cataloging planets. It is a deeply human endeavor to connect across incomprehensible distances, to seek understanding, and to nurture hope. Every drop of water found, every data point on atmospheric composition, every modeled ocean depth draws us closer to a cosmic story that, one day, may reveal fundamental truths about life in the universe. This narrative, quiet, expansive, and filled with wonder, invites us to set aside the rush of daily life and step into a calmer, more reflective space. Together, we will delve deeply into the intricacies of Gliese 1214b and ocean planets in general, unfolding mysteries slowly and deliberately, like the gentle tides of an alien sea. It is a journey of knowledge and imagination, one that invites curiosity not just as a fleeting excitement, but as a sustained, almost meditative exploration of distant worlds. With our minds open and our pace unhurried, we prepare to leave behind the familiar and enter the vast, mysterious realms of alien oceans and distant stars, forever expanding the frontiers of human understanding and dreaming. The discovery of Gliese 1214b marked a significant milestone in the field of exoplanetary science, opening a new chapter in our understanding of the diversity and complexity of planets beyond our solar system. At its core, this discovery introduced humanity to a new category of exoplanets that did not quite resemble the gas giants like Jupiter or the smaller rocky planets like Earth. Instead, Gliese 1214b emerged as an example of a super-Earth, or mini-Neptune, a fascinating hybrid whose very existence expands the boundaries of how we classify and imagine distant worlds. To appreciate the impact of Gliese 1214b's discovery, it helps to consider the context of exoplanet hunting at the dawn of the 21st century. In the late 1990s and early 2000s, astronomers had just begun confirming the presence of planets orbiting other stars, mostly massive Jupiter-sized bodies, often tightly hugging their stars in scorching orbits. Detecting smaller Earth-sized planets was far more difficult due to limitations in both technology and observational methods. Yet scientists knew these smaller planets must be out there, perhaps even more numerous, and their detection would be key to understanding planetary formation and the prospects for life elsewhere. Gliese 1214b was discovered in 2009 by a team led by David Charbonneau, utilizing the MERTH project, a ground-based survey aimed specifically at detecting small planets orbiting nearby red dwarf stars. The MERTH project's strategy was ingenious. Red dwarfs are smaller and cooler than the Sun, making it easier to detect the subtle dimming of starlight when a planet transits or passes in front of its host star. In this instance, the team observed periodic dips in brightness from Gliese 1214, a red dwarf star about 48 light-years away in the constellation Ophiuchus. These dimming events corresponded to a planet with a radius approximately 2.6 times that of Earth, and with further data, the planet's mass was estimated to be around 6.5 times Earth's mass. This combination of mass and size placed Gliese 1214b squarely within the realm of super-Earths. But that alone was not the entire story. When astronomers computed its density, they found it significantly lower than that of Earth. This suggested that the planet couldn't be purely rocky. Rather, it must contain substantial amounts of water, volatiles, or gases lighter than rock and iron. In simple terms, Gliese 1214b seemed to be thicker and less dense than Earth, pointing towards a world that could be enveloped with a massive atmosphere or even vast oceans. This was a striking revelation, signaling a possible new class of planet with characteristics distinct from anything previously studied. The discovery was notable not only because of what Gliese 1214b was, but because of where it was found. Situated close to its host star, with an orbital period of just over 1.5 days, this planet challenges our Earth-centric expectations about habitability and atmosphere. Its proximity means it is likely tidally locked, presenting one face perpetually to its star, resulting in extreme temperature gradients. These conditions complicate the potential nature of its surface and atmosphere, yet also provide a valuable laboratory for understanding planetary physics under conditions enormously different from those on Earth. One of the reasons Gliese 1214b captivated the scientific community so thoroughly is its relative accessibility for observation. Being relatively close in astronomical terms and orbiting a small star bright enough in the infrared made it a prime candidate for atmospheric characterization. This enabled subsequent observations using space telescopes like the Hubble, and eventually preparations for study with the James Webb Space Telescope, promising insights into the composition and dynamics of an alien atmosphere, possibly even signs of water vapor or clouds. Moreover, the discovery of Gliese 1214b revitalized theoretical models of planet formation and structure. It called into question simplistic distinctions between rocky terrestrial planets and gaseous giants, highlighting the need to understand a wider spectrum of planetary compositions and atmospheric behaviors. Scientists began to explore the possibility that ocean planets, with deep, global layers of water or other ices, could exist in large numbers throughout the galaxy, each with unique evolutionary histories. This realization urged astronomers to reconsider the criteria for planetary habitability, as ocean worlds like Gliese 1214b might harbor environments stable for life of a radically different kind than life on Earth. The speculative nature of such possibilities fueled exciting theoretical, observational, and even philosophical work, weaving together astrophysics, geophysics, atmospheric chemistry, and astrobiology. In summary, the discovery of Gliese 1214b was more than the detection of just another distant planet. It announced a new frontier in exoplanet exploration, a class of planets where water or thick atmospheres dominate in ways previously unimaginable. From the initial detection of its transit across a nearby red dwarf star to the extensive studies that followed, Gliese 1214b provides a compelling glimpse into the multitude of planetary varieties the cosmos holds. It invites us not only to marvel at the richness and complexity of worlds beyond our own, but to ponder the fundamental question of what it truly means to be a planet, and whether some of these remote, water-laden worlds might, in ways we have yet to grasp, be places of life or precursors to life. As we move forward in this journey, having set the discovery of Gliese 1214b at the heart of our exploration, we prepare to delve deeper into the nature of super-Earths, the characteristics of its parent star, and the observational techniques that have allowed us to unravel its mysteries. This discovery sets the stage for a fascinating narrative of discovery, inquiry, and cosmic wonder. As we deepen our exploration of Gliese 1214b, it becomes essential to place this intriguing exoplanet within the broader context of its classification, that of a super-Earth. This term, while it may sound straightforward, actually encompasses a diverse and complex class of planets that challenge our conventional understanding of planetary types. To truly grasp the significance of Gliese 1214b, we need to meticulously unpack what defines a super-Earth, explore the characteristics shaped by their size and mass, and understand the nuances of their classification within the vast menagerie of known exoplanets. At its core, the label super-Earth refers to an exoplanet whose mass and size lie somewhere between Earth and the ice giants, such as Uranus and Neptune. Typically, a super-Earth has a mass ranging from about 1.5 to 10 times that of Earth, and a radius up to about 2 to 3 times Earth's. However, these numerical boundaries are not rigid. Rather, they provide a general framework that helps astronomers categorize planets that are larger than Earth, but significantly smaller than gas giants. This distinction is vital because it hints at fundamental differences in planetary composition, structure, and potential habitability. While one might assume that a super-Earth is simply a scaled-up Earth, the reality is more nuanced. As planetary mass increases, gravitational compression intensifies, potentially affecting the planet's density and internal structure in intricate ways. For instance, a planet with a mass 5 times that of Earth might not be 5 times the size due to the compressive effects on its interior materials. Simply put, mass and radius data can only tell part of the story. Density calculations derived from these measurements often reveal surprising insights about a planet's composition. Whether it is predominantly rocky, icy, or gaseous, super-Earths occupy a transitional region between terrestrial planets and gas giants. Some may be primarily rocky, with solid surfaces and thin atmospheres, somewhat resembling Earth but generally exhibiting stronger gravity and potentially more intense geological activity. Others might possess significant volatile layers, thick atmospheres rich in hydrogen and helium, or extensive oceans of water and other ices, making them more akin to miniature versions of Neptune, often referred to as mini-Neptunes. This diversity within the super-Earth category complicates efforts to generalize about these worlds. For example, 2 planets with similar sizes might differ drastically if one is primarily rocky, while the other is enveloped by a thick, gaseous atmosphere. This matter becomes particularly significant when discussing habitability because the presence and nature of an atmosphere strongly influence surface temperatures, radiation levels, and chemical environments, all critical factors for life as we understand it. The classification of super-Earths relies heavily on observational techniques that measure key parameters: mass, radius, and orbital characteristics. Transit observations, which detect minute dips in a star's brightness as a planet passes in front, yield the planet's radius. Radial velocity measurements track the subtle gravitational wobble imposed on a star by an orbiting planet, providing mass estimates. Combining these methods allows astronomers to approximate a planet's density. When density suggests a predominantly rocky composition, the planet is closely aligned with what we think of as terrestrial. Conversely, lower densities indicate envelopes of thick atmospheres or large quantities of water and volatiles. Gliese 1214b exemplifies the intriguing complexity of super-Earths. Its radius is about 2.6 times that of Earth, and its mass roughly 6.5 times greater. These figures place it firmly within the super-Earth range, but its relatively low density suggests it is not a purely rocky planet. Instead, it likely possesses a substantial envelope of gases or an extensive water layer, leading scientists to speculate about it being an ocean planet or a mini-Neptune. Understanding super-Earths is not merely an academic exercise. It reshapes fundamental theories of planet formation and evolution. The realization that such planets are common throughout the galaxy, more so than Earth-size planets or gas giants in many cases, prompts questions about why our solar system lacks true super-Earths. Models of protoplanetary disks, planetary migration, and atmospheric retention have been adapted and refined to accommodate this class of planets, offering a broader picture of how diverse planetary systems can be. Additionally, studying super-Earths expands the scope of habitable worlds. While a super-Earth's increased gravity might present challenges for habitability, such as denser atmospheres or intense geological activity, its larger size often provides a more substantial atmosphere and potential for persistent liquid water, assuming the right orbital conditions. The combination of these factors suggests that while not all super-Earths are habitable, some might offer stable environments capable of supporting life, albeit potentially quite different from what we know. The classification of super-Earths also intersects with the field of atmospheric characterization. Observing the atmospheres of these planets reveals clues about composition, weather patterns, and possible biosignatures. For Gliese 1214b, extensive studies have been conducted to detect water vapor, methane, or other gases that might indicate complex atmospheric chemistry or even biological processes. Although definitive signs of life remain undiscovered, the mere possibility of such complexity elevates the importance of super-Earth studies. In the quest to classify and understand super-Earths, astronomers also employ numerical simulations and theoretical modeling. These approaches test various compositions and atmospheric scenarios against observational data, allowing researchers to constrain what kinds of internal and external conditions are plausible for any given planet. Challenges arise, however, when degeneracies exist. That is, when multiple compositions yield similar density measurements, making it difficult to conclusively determine a planet's makeup without further data. Ultimately, the study of super-Earths represents a dynamic frontier in planetary science. These planets blur the lines between familiar categories and compel us to reconsider our assumptions about planetary formation, structure, and habitability. Gliese 1214b stands as a fascinating case study, a planet whose size and mass invite curiosity and whose enigmatic nature challenges scientists to unravel the mysteries of alien worlds. In our unfolding exploration, understanding super-Earths like Gliese 1214b sets the stage for examining the unique characteristics of its host star and the cosmic environment in which it resides. This foundation will prove invaluable as we probe deeper into the detection methods and the orbital dance that shape the nature of this remarkable exoplanet. Our journey into the enigmatic world of Gliese 1214b naturally leads us to first become acquainted with its home star, Gliese 1214, and the broader cosmic neighborhood in which this fascinating planetary system resides. Understanding the star is crucial because it shapes the environment and evolution of its planets, particularly Gliese 1214b, whose properties are intimately tied to the nature of their stellar host. By exploring the characteristics of Gliese 1214 and the context of its surrounding stars, we gain vital perspective on how ocean planets like Gliese 1214b fit within the rich and diverse fabric of our Milky Way galaxy. Gliese 1214 is classified as an M-type red dwarf star. Red dwarfs rank among the most common and long-lived stars in our galaxy, representing roughly 70 to 75% of all stars. Their small sizes and cool temperatures set them apart from stars like our Sun. With a mass approximately 1/5 that of the Sun and a radius roughly 1/4 as large, Gliese 1214's luminosity, its total energy output, is only about 0.3 to 0.4% that of our own star. This relatively modest energy production creates conditions on nearby planets that differ markedly from those in systems orbiting larger, hotter stars. Situated approximately 48 light-years away in the constellation Ophiuchus, Gliese 1214 is a neighboring star by cosmic standards, making it quite accessible for study with modern telescopes. Despite its faintness to the naked eye, astronomers have been able to characterize it well through spectroscopy, a technique analyzing the light it emits in various wavelengths to deduce the star's composition and properties. Gliese 1214's surface temperature is estimated to be around 3,000 Kelvin, significantly cooler than the Sun's roughly 5,800 Kelvin. This cooler temperature results in a redder hue, hence the term red dwarf. What makes red dwarfs like Gliese 1214 especially interesting in the search for exoplanets is their longevity. These stars burn their fuel at a sluggish pace compared to more massive stars, allowing them to exist for trillions of years, a span that far exceeds the current age of the universe. Consequently, any planets orbiting such stars have the potential for very long-term stability, raising tantalizing questions about the possibility of life developing and evolving over extraordinarily long timescales in these systems. The immediate cosmic neighborhood of Gliese 1214 is similarly populated predominantly by other small stars. The local region within 50 light-years of Earth, sometimes called the solar neighborhood, is rich with red dwarfs, white dwarfs, and a scattering of more massive stars. Unlike the crowded star clusters or bustling spiral arms deeper in the galaxy, this neighborhood offers a relatively tranquil stellar environment, which minimizes the likelihood of close stellar encounters or harsh radiation events that could disrupt planetary systems. This makes Gliese 1214's neighborhood a stable laboratory for studying planet formation and evolution. The planetary system of Gliese 1214 itself appears relatively simple compared to our own. So far, only one confirmed planet is known: Gliese 1214b. The search for additional worlds around this star continues, as multiple planets are common around red dwarfs, but none have yet been confirmed or announced for this particular system. This singular companion planet orbits very closely to the star, completing a revolution in about 1.58 Earth days. Such a tight orbit places Gliese 1214b far nearer to its star than Mercury is to the Sun, exposing it to strong stellar effects despite the star's lower luminosity. The tight orbital proximity raises compelling questions about the evolutionary history of Gliese 1214b. Was it always so close to its star, or did it migrate inward through gravitational interactions? Such migrations are common in planetary systems, especially around red dwarfs, where protoplanetary disks can have diverse mass distributions and dynamics. Its close orbit means the planet is likely tidally locked, with one hemisphere in constant daylight and the other in permanent night, conditions that significantly affect atmospheric circulation, temperature gradients, and possibly chemistry on and above its surface. From a broader galactic perspective, Gliese 1214 resides in the thin disk of the Milky Way, a relatively young and metal-rich region conducive to planet formation. Metals, in astronomical parlance, denote all elements heavier than helium, which are essential building blocks for the formation of rocky planets and the complex chemistry that fosters rich atmospheres. The chemical composition of Gliese 1214 suggests it possesses sufficient metals to have formed planets with varied compositions, possibly including substantial water content. The spectral measurements of Gliese 1214's light provide insights not only into the star's composition, but also into its activity level. Red dwarfs are known for magnetic activity, including stellar flares that can dramatically affect orbiting planets by bombarding them with high-energy radiation and particles. While Gliese 1214 is classified as a relatively inactive star compared to other red dwarfs, it does exhibit some degree of variability. This has direct implications for Gliese 1214b's atmosphere and potential habitability, highlighting the intricate dance between star and planet. Astronomers have also observed Gliese 1214 in different wavelengths, from visible and infrared light to X-rays, to paint a fuller picture of its properties and behavior. The infrared observations are particularly valuable because red dwarfs emit the majority of their light in these longer wavelengths, enabling precise measurements of both the star's brightness and the signatures imprinted when its planet transits across its face. Because of its small size and relatively dim light output, Gliese 1214 provides a favorable contrast for detecting and studying planets like Gliese 1214b. The planet's transit creates a deeper and more readily measurable dip in starlight compared to a similar planet orbiting a larger, brighter star. This advantage has made Gliese 1214 one of the most scrutinized stars in exoplanetary investigations, with observations aiming to decipher the mysteries of its intriguing planet's atmosphere and composition. Despite the advances in understanding Gliese 1214, many questions remain. Does the star host additional planets too small or too distant to have been detected yet? How does the star's magnetic activity vary over longer timescales? And what effect might this have on its planet? Could the star's age and chemical makeup offer clues about the formation history of its planetary companion? These open questions make Gliese 1214 a star of continuing interest and a window into the nuanced relationship between stars and their planets. In essence, meeting Gliese 1214, the relatively cool, small, and long-lived red dwarf star, and situating it within its quiet cosmic neighborhood, allows us to appreciate the conditions under which Gliese 1214b exists. This understanding frames the challenges and opportunities that come with studying ocean planets in such systems. It reminds us that every planet we explore is not isolated, but intricately woven into the story of its stellar environment, which shapes its destiny in myriad ways. As we prepare to look even closer at how Gliese 1214b was detected and studied, this foundational knowledge of its star and surroundings will enrich our appreciation of the methods and results, ground our journey in context, and deepen the sense of wonder as we peer into the distant waters of this mysterious and captivating world. Delving deeper into the captivating story of Gliese 1214b inevitably directs our attention to the remarkable methods by which this distant world revealed itself to us. The discovery and subsequent observations of Gliese 1214b not only broadened our catalog of known exoplanets, but also showcased the power of innovative techniques in the detection and characterization of alien worlds. To truly appreciate the richness of the knowledge we have about this ocean planet candidate, it is vital to understand how astronomers first detected Gliese 1214b and how they have since meticulously probed its presence and properties. The primary method responsible for the unearthing of Gliese 1214b was the transit method, an elegant and profoundly insightful tool that has revolutionized exoplanetary science in recent years. The fundamental principle behind this technique centers around the observation of a star's brightness over time. When a planet crosses, or transits, the face of its host star from our vantage point here on Earth, it causes a slight but measurable dimming of the star's light. By carefully monitoring these periodic dips, astronomers can infer the presence of a planet, its orbital period, and its size relative to the star. Gliese 1214b was discovered in 2009 by an international team of astronomers led by David Charbonneau of the Harvard-Smithsonian Center for Astrophysics. The discovery arose from data gathered by the MERTH project, an ambitious ground-based endeavor specifically aimed at detecting Earth-size and super-Earth exoplanets orbiting nearby red dwarf stars. The rationale behind focusing on red dwarfs is rooted in their small size and low luminosity, which amplify the relative change in brightness caused by planetary transits, making it easier to detect even small planets. The MERTH project employs an array of robotic telescopes situated at the Fred Lawrence Whipple Observatory in Arizona, continuously monitoring hundreds of nearby red dwarf stars. In the case of Gliese 1214, astronomers detected a pattern of diminutions in brightness recurring steadily every 1.58 days. This rapid periodicity indicated that a planet was orbiting extraordinarily close to its host star, completing an orbit in less than 2 Earth days. The measured depth of the dip, the fractional amount by which the star's light diminished during the transit, allowed researchers to calculate the planet's radius as approximately 2.6 times that of Earth. Detection by the transit method establishes the planet's size, but leaves the planet's mass uncertain. To gain insights into the mass, astronomers turn to the radial velocity technique. This method takes advantage of the gravitational pull that a planet exerts on its star. Although the star is overwhelmingly massive compared to the planet, the star wobbles slightly due to the planet's tug, as both orbit their common center of mass. By observing shifts in the star's spectral lines, minute changes in the wavelengths of light it emits, scientists can measure this wobble and thus estimate the planet's mass. Following the initial identification of Gliese 1214b, radial velocity measurements were carried out using some of the world's most sensitive spectrographs, including the HARPS instrument mounted on the 3.6-meter telescope at the European Southern Observatory in Chile. These observations provided a mass estimate of approximately 6.5 Earth masses for Gliese 1214b, complementing the radius measurement from the transit data and facilitating calculations of the planet's average density. The combination of the transit and radial velocity methods allowed astronomers not only to confirm the planetary nature of Gliese 1214b, but also to begin inferring its composition. Its mean density, intriguingly less than Earth's but greater than that of gas giants, suggested that the planet is neither a purely rocky world nor a typical gas giant, but something intermediate, likely adorned with thick atmospheres or substantial layers of water. Beyond the initial discovery, astronomers continued to utilize the transit method to study the planet's atmosphere through transit spectroscopy. This technique observes the star's spectrum during a planet's transit to detect the chemical fingerprints of its atmosphere. When the planet passes in front of the star, a portion of starlight filters through the planet's atmospheric limb, the thin ring of atmospheric gases surrounding it. Molecules absorb light at specific wavelengths, leaving characteristic imprints in the star's spectrum, which astronomers analyze to deduce atmospheric composition. Gliese 1214b's atmosphere has been the subject of intensive study, especially with space telescopes like the Hubble Space Telescope. Observations have sought to detect water vapor, methane, carbon dioxide, and other gases that could hint at the planet's surface environment and possible oceanic features. The results, while intriguing, have often been ambiguous, partly due to the presence of clouds or haze that obscure spectral features and complicate interpretation. In addition to optical and near-infrared observations, astronomers have employed techniques involving measurements in other electromagnetic bands, such as the infrared, to probe the thermal emission from Gliese 1214b. These measurements help gauge the planet's temperature, albedo, reflectivity, and atmospheric dynamics, further enriching the model of its physical and chemical environment. The detection and characterization of Gliese 1214b represent a symphony of complementary methodologies. Each technique, from ground-based transit photometry and radial velocity spectroscopy to space-based atmospheric spectroscopy, has contributed an invaluable piece to the puzzle. Collectively, they transform a faint, distant dot of light in the sky into a tangible world with measurable radius, mass, atmospheric composition, and orbital parameters. This remarkable achievement is a testament to the strides made in astronomical instrumentation, observational strategy, and data analysis techniques over the past few decades. It demonstrates the extraordinary capacity of humanity to detect and study worlds tens of light-years away, despite our limited means of direct exploration. Looking ahead, the techniques refined and proven in the study of Gliese 1214b anticipate an exciting era of discovery. Future observatories, such as the James Webb Space Telescope and next-generation ground-based instruments, promise even more detailed atmospheric characterization, possibly revealing the nature of the mysterious clouds or oceans that might cover this super-Earth. These advances will deepen our understanding of alien worlds and inch us closer to answering profound questions about planetary diversity and the potential for life beyond Earth. As we continue this exploration, the careful dance of observation and interpretation that brought Gliese 1214b into human awareness stands as an inspiring example of scientific perseverance and ingenuity. With every new technique and observation, we peel back layers of mystery, revealing the intricate dynamics of distant solar systems and the potential habitability of oceanic exoplanets in our galactic neighborhood. Gliese 1214b's orbit is a compelling subject in itself, a fascinating orchestration of celestial mechanics that defines not only where the planet resides in its star system, but also shapes its environmental conditions in profound ways. As we begin to understand this exoplanet's close dance with its red dwarf star, we gain not only insight into its physical setting, but also crucial clues about the complex interactions that govern the nature of ocean planets orbiting small, cool stars. One of the defining characteristics of Gliese 1214b's orbit is its extremely short period. It completes one full revolution around its host star in just about 1.58 Earth days. To put this in perspective, our closest planet, Mercury, takes roughly 88 days to orbit the Sun, which means that Gliese 1214b whirls around its star approximately 55 times faster. This swift orbit indicates an extremely tight proximity to Gliese 1214. The star's gravitational pull firmly governs the planet at a distance roughly 20 times closer than Earth is to the Sun. This intimate relationship has profound implications for everything from the planet's climate to its internal dynamics. Because of the closeness, Gliese 1214b is almost certainly tidally locked to its star, a phenomenon familiar to us through the Earth's moon, which perpetually shows the same face to our planet. For Gliese 1214b, this means that one hemisphere experiences continuous daylight, bathed in the soft red glow of its star, while the other endures permanent night. This peculiar state generates extreme temperature contrasts between the day and night sides, potentially fueling intense atmospheric circulation as heat attempts to redistribute around the globe. In planetary atmospheres, such heat transport can lead to dynamic weather patterns markedly different from those on Earth. In addition to tidal locking, the close orbit subjects Gliese 1214b to intense gravitational forces, resulting in tidal heating. This process arises as the star's gravity stretches and flexes the planet's interior, generating internal friction and heat, akin to what happens on Jupiter's moon Io. Tidal heating can influence geological activity, perhaps sustaining a subsurface ocean beneath icy layers, or driving volcanic or tectonic activity, which in turn could affect the atmospheric composition and dynamics. The proximity to the red dwarf star also exposes Gliese 1214b to various forms of stellar radiation, including ultraviolet light and, potentially, charged particle flows from stellar winds and flares. Despite red dwarfs generally being cooler and less luminous than the Sun, their stellar activity can be more volatile, especially during their younger stages. This radiation environment can erode planetary atmospheres or drive chemical reactions in the atmospheric layers, playing a pivotal role in defining the planet's habitability and surface conditions. However, Gliese 1214 appears to be a relatively quiet red dwarf, which might help shield its planet from the most extreme flare events. An additional factor influenced by the orbit is the planet's energy budget, the balance between the energy it receives from the star and the energy it radiates back into space. Although the star's luminosity is only a fraction of the Sun's, Gliese 1214b's close distance compensates to deliver significant stellar energy. The calculated equilibrium temperature of the planet hovers around 400 to 600 Kelvin, approximately 127 to 327 degrees Celsius, a range distinctly hotter than Earth's, yet within conditions where, under the right atmospheric pressure, liquid water or exotic forms of supercritical fluids could exist. This opens the tantalizing possibility that the planet might possess global oceans, albeit under very different thermodynamic regimes from terrestrial seas. Moreover, the red dwarf's spectral output is heavily weighted toward the infrared. This affects how energy is absorbed and re-radiated by the planet's atmosphere and surface. Absorptive gases like water vapor and methane interact particularly strongly with infrared radiation, shaping the greenhouse effect on Gliese 1214b. Depending on atmospheric composition and cloud cover, this greenhouse effect can significantly modify surface or ocean temperatures, either intensifying heat retention or causing complex feedback mechanisms within the climate system. Orbital eccentricity is another important parameter influencing Gliese 1214b's environment. Current observations suggest that, unlike highly elliptical orbits that produce extreme seasonal variations, Gliese 1214b's orbit is likely close to circular. This stable orbit reduces temperature swings due to varying stellar distance, potentially fostering more consistent conditions. However, slight deviations could still produce notable effects when coupled with tidal heating and atmospheric dynamics. The close stellar environment also affects the planet's magnetosphere, or perhaps the lack thereof. The magnetic field generated internally by a planet helps shield it from charged particles emitted by the star. For Gliese 1214b, how a close orbit affects its magnetic field remains uncertain. If the planet retains a strong magnetosphere, it would help preserve its atmosphere and surface water over long periods. Conversely, a weak or absent magnetosphere could lead to atmospheric stripping by stellar winds, drastically altering its environment. This intimate stellar embrace also influences the potential for observational studies. The tight, rapid orbit results in frequent transits, offering astronomers repeated opportunities to observe Gliese 1214b crossing its star. From these repeated transits, scientists derive high-quality data about the planet's size, atmospheric transmission spectra, and even thermal emissions. The stability and predictability of the orbit thus enhance our capacity to probe this distant world and refine our models of its nature. In sum, Gliese 12-14b's orbit is a defining feature in its story. A close, rapid dance around a cool red dwarf star that governs its environmental conditions, internal processes, and observational characteristics. From tidal locking and heating to the interplay of stellar radiation and atmospheric physics. This relationship shapes a world that may harbor vast oceans under alien skies, sculpted by forces both familiar and extraordinary. As we continue, this understanding of orbit and environment prepares us to delve deeper into the physical properties that hint at the planet's internal composition and the nature of its possible oceans. As we deepen our inquiry into Gliese 12-14b, one of the most illuminating approaches involves examining its fundamental physical properties: mass, radius, and density. These measurements serve as essential keys, unlocking clues about the planet's internal composition, structural makeup, and the possible nature of its enigmatic surface. Through these vital parameters, astronomers piece together an intricate portrait of a world that is at once familiar in concept, yet utterly alien in detail. Let us begin with the planet's radius, which was precisely determined through transit observations. When Gliese 12-14b passes in front of its host star, the star's brightness temporarily diminishes. The amount of dimming directly relates to the size of the planet relative to the star. Through meticulous repeated measurements, astronomers established that Gliese 12-14b's radius is approximately 2.6 times that of Earth. This is significant because the planet is distinctly larger than our homeworld, but not so large as to resemble the vast gas giants like Jupiter or Saturn. This intermediate size places it in the super-Earth category, suggesting an intriguing blend of characteristics. Complementing the radius is the planet's mass, measured using the radial velocity method. This technique observes the gravitational tug a planet imparts on its star, causing subtle but detectable wobbles. For Gliese 12-14b, these observations yielded a mass of roughly 6.5 Earth masses. When combined with its radius, this leads us to calculate its average density, a fundamental physical property that sheds light on what the planet is made of. Density, essentially mass divided by volume, allows scientists to infer the overall composition of a planet. Earth, a rocky terrestrial planet, has an average density of about 5.5 grams per cubic centimeter. In contrast, gas giants like Jupiter have much lower densities, about 1.3 grams per cubic centimeter, due to their massive envelopes of hydrogen and helium. Gliese 12-14b's density falls notably somewhere between these extremes, at approximately 1.9 to 3 grams per cubic centimeter. This intermediate density hints that the planet cannot be solely rocky nor completely gaseous. Instead, it points to a complex composition, likely including a mix of rock, water, and gaseous layers. This relatively low density, compared to Earth, signals that Gliese 12-14b might harbor a significant amount of volatiles, chemical compounds with low boiling points such as water, ammonia, or methane, that constitute thick atmospheric layers or extensive oceans. The planet is too dense to be a gas giant, yet its density is too low to be a purely terrestrial world, suggesting something akin to a water-rich planet or a mini Neptune cloaked in a thick gaseous layer. Scientists have constructed various interior models to explore plausible compositions consistent with Gliese 12-14b's measured properties. Some models propose a planet with a rocky core surrounded by a deep ocean, hundreds of kilometers thick, underlying an atmosphere perhaps rich in water vapor, or hydrogen and helium. Other models speculate about a dense, hydrogen-helium-rich envelope enveloping an ice or rock interior. The challenge in these analyses arises because different combinations of rock, water, and gas can produce similar overall densities, leading to degeneracies in interpretation. Another intriguing aspect is the influence of pressure on the planet's interior. Given Gliese 1214b's mass and size, the pressure in its deep interior must be immense, far exceeding pressures found in Earth's core. Under such conditions, water behaves differently, potentially forming exotic high-pressure ice phases or supercritical fluids that do not exist naturally on Earth's surface. Understanding these possibilities helps envision the internal layering of the planet, from a solid or semi-solid core to fluid or ice mantles, and eventually to the outer atmosphere. The precise measurement of the planet's radius and mass has driven intense efforts to characterize its atmosphere through transit spectroscopy, which could discriminate between competing composition hypotheses. For instance, a hydrogen-rich, low molecular weight atmosphere would present distinctive spectral features detectable by telescopes. Conversely, a heavy, water-rich atmosphere or thick clouds could obscure such features, impacting density interpretations indirectly. Analyzing the planet's density also helps assess its potential for habitability or the presence of liquid water. While the planet's temperature, determined largely by its stellar environment, is a critical factor, composition influences whether liquid water might exist beneath clouds or ice layers. Gliese 1214b's relatively high temperature suggests surface conditions that are challenging for life as we know it. Yet its substantial volatile content keeps open the fascinating possibility of exotic ocean worlds. In the broader landscape of exoplanetary science, Gliese 1214b's physical properties enrich the diversity of known planets, bridging the gap between Earth-like worlds and gas giants. This bridge prompts us to refine planetary classification, models of planetary formation, and theories about atmospheric retention. Importantly, it illustrates that mass and radius measurements, combined with density calculations, form the cornerstone of our capacity to understand distant worlds with no direct imaging yet possible. As we transition to hypothesizing about Gliese 1214b's surface conditions and atmosphere, these physical properties provide a compass guiding subsequent inquiry. The mass, radius, and especially the inferred density ground our exploration in measurable reality, setting the stage for unraveling one of the most captivating mysteries. Does Gliese 1214b possess a global ocean beneath its clouds, or is it dominated by an atmosphere thick with exotic gases? This question, poised at the intersection of observation and theory, lies at the heart of the ocean-planet enigma. As we turn our gaze toward Gliese 1214b's surface, we enter one of the most intriguing and active debates in exoplanetary science. Does this distant world possess a thick, gaseous atmosphere cloaking a rocky core? Or is it, as some models propose, an ocean planet enveloped by vast global seas beneath clouds that might defy earthly experience? This question lies at the heart of our quest to understand Gliese 1214b and serves as a gateway to imagining alien environments that challenge our everyday perceptions of what a planet's surface might be like. The essence of the atmosphere or ocean dilemma stems from the planet's measured physical properties, especially its low average density compared to Earth. This density suggests the presence of elements or compounds lighter than rock and iron that contribute significantly to the planet's volume. Two main scenarios have been prominently discussed by scientists over the past decade. One envisioning an extensive, hydrogen and helium-rich atmosphere overlaying a rocky and possibly watery interior, and the other proposing a so-called water world dominated by deep oceans, possibly hundreds of kilometers thick, where exotic phases of water might prevail. In the first scenario, Gliese 1214b is conceptualized as a mini-Neptune, featuring a dense, rocky core perhaps similar in composition to Earth, but surrounded by a substantial gaseous envelope. This atmosphere would be primarily hydrogen and helium, primordial gases captured during the planet's formation. Such a layer could be several hundred kilometers thick, exerting tremendous pressure on any underlying solid or liquid interiors. The presence of a hydrogen-rich atmosphere would have wide-ranging effects on the planet's climate, radiation environment, and potential for supporting life as we know it. Observations aimed at characterizing this atmosphere have yielded both tantalizing clues and puzzling ambiguities. Using transmission spectroscopy, analyzing the starlight filtered through the planet's atmosphere during transit, astronomers have sought signatures of common gases such as water vapor, methane, and carbon dioxide. However, early observations frequently resulted in a flat or featureless spectrum, which could indicate a thick, cloud-covered atmosphere masking gaseous absorption lines. These clouds, or hazes, might be composed of photochemically produced particles or condensates exotic to the planet's unique environment. The alternative hypothesis imagines Gliese 1214b as a true ocean planet, where water is the dominant constituent not just superficially, but throughout a significant fraction of the planet's mass. In this vision, rather than being sealed beneath a thick hydrogen envelope, the planet's surface might be an ocean extending to enormous depths, far beyond Earth's deepest trenches, possibly enveloped in high-pressure ice layers or supercritical fluids due to intense heat and pressure. Such an ocean world could be largely shrouded in a dense atmosphere rich in water vapor, generating a visual appearance of clouds and thick mist. Ocean planets, in theory, possess intriguing physical states, with potential layers of liquid water overlain or interspersed by exotic ices like Ice 7th or Ice X, crystalline phases stable only under pressures millions of times that on Earth's surface. The interface between ocean and atmosphere under these conditions is unlike any known earthly environment and complicates predictions about weather, climate, and potential chemistry. Both hypotheses present strong scientific foundations, but also inherent challenges. For the thick hydrogen-helium atmosphere to persist over billions of years, the planet must have avoided or successfully replenished atmospheric loss mechanisms like stellar wind stripping, which can be severe given Gliese 1214b's proximity to its active red dwarf star. Conversely, sustaining a deep global ocean requires considerable water inventory, which must have been incorporated early in the planet's history or delivered later via impacts or outgassing. The nature of Gliese 1214b's surface also depends strongly on the complex interplay of atmospheric pressure, temperature, and chemical composition. At temperatures estimated between roughly 400 and 600 Kelvin, water may exist not as familiar liquid seas, but as supercritical fluid, a state neither fully liquid nor gas, with intriguing implications for heat transport and chemistry. It's worth noting the limitations faced by astronomers in conclusively distinguishing between models. The planet's relatively faint host star and the presence of clouds or hazes complicate spectral measurements, requiring ever more sensitive instruments. Future missions and telescopes, such as the James Webb Space Telescope, promise to bring higher resolution and broader wavelength coverage to bear on this mystery, potentially distinguishing between a hydrogen-rich atmosphere and a water-dominated world. Beyond atmosphere and ocean, a hybrid scenario is also conceivable. A planet with a modest hydrogen-helium envelope punctuated or overlain by thick water layers and complex cloud formations, creating a unique environment where lessons from both ocean and gas giant worlds intersect. In contemplating this tantalizing uncertainty, we not only stretch the boundaries of planetary science, but also evoke broader philosophical reflections. What does it mean to classify a planet as an ocean world? Could life thrive under such alien oceanic conditions, distinctly different from Earth's seas? How might these layers and atmospheres shape the planet's climate feedbacks and evolution over time? Thus, the atmosphere or ocean question on Gliese 1214b exemplifies both the excitement and the challenge of exoplanetary science. The challenge to infer the nature of unseen, distant worlds from faint flickers of starlight, and the excitement of confronting realities far stranger yet profoundly linked to our own planet's watery heritage. It is a captivating puzzle, inviting us to consider forms of planetary environments that defy easy categorization and promise to reshape our understanding of planetary diversity in the galaxy. As we move forward, these hypotheses about Gliese 1214b's surface and atmosphere will serve as a foundation for exploring the broader concept of ocean planets, worlds where water shapes destiny in realms stretching far beyond the familiar shores of Earth. The concept of ocean planets, sometimes called water worlds, represents a fascinating and expanding area of planetary science that challenges traditional classifications and deepens our understanding of planetary diversity across the cosmos. These hypothetical worlds are characterized by surfaces dominated chiefly by water, often featuring global oceans that may be many kilometers or even hundreds of kilometers deep, without the kind of continental land masses we see on Earth. The theoretical frameworks and predictions underlying the idea of ocean planets emerged gradually as astronomers and planetary scientists studied the chemical and physical processes involved in planet formation, evolution, and habitability. Theoretical models suggest that ocean planets could form in a variety of ways. One scenario involves a protoplanetary disk composed of gas, dust, and ices, rich in water and volatiles beyond the so-called snow line, the distance from a star where temperatures are low enough for water to condense into ice. Planets that form in or migrate through this zone can accumulate significant amounts of water ice in addition to rock and metal. If these planets possess sufficient mass to retain these volatiles, but not so much as to balloon into gas giants, they can develop thick water layers that melt into vast oceans under the heat of their star or internal geothermal processes. Another intriguing formation pathway involves the migration of icy and watery bodies from the outer regions of planetary systems inward toward their stars, where increased temperatures melt ices, generating liquid oceans and thick water atmospheres. This idea aligns with theories of planetary migration, which have become critical in explaining the surprising diversity of exoplanet orbits observed. Predictions about ocean planets' physical structure emanate from combining models of interior dynamics, composition, and thermodynamics. Typically, these planets are envisaged with a layered internal structure. A rocky or iron core may be overlain by a thick mantle of high-pressure ices or fluid water. Above this mantle may be an immense global ocean, topped by a dense atmosphere potentially rich in water vapor or other volatiles. The depth and pressure within these oceans would far exceed Earth's, producing exotic phases of water such as supercritical fluids and high-pressure ices unknown on Earth's surface. One of the most compelling aspects of ocean planets is their potential to broaden the criteria for habitable worlds. On Earth, liquid water is fundamental to life. The notion that entire planets might be enveloped in water suggests vast habitats for life, albeit in forms and conditions possibly very different from terrestrial life. For instance, life in the deep oceans of these worlds could exist without sunlight, similar to Earth's hydrothermal vent ecosystems, sustained instead by chemical energy from the planet's interior. Predictive models also explore the atmospheric characteristics of ocean planets. Depending on factors like stellar radiation, planetary mass, and volcanic activity, these atmospheres might range from thick, water vapor-rich envelopes generating greenhouse effects to thinner, cloud-dominated covers that regulate surface temperatures. Cloud composition and dynamics could be exotic. For example, clouds composed of complex hydrocarbons or other exotic condensates formed under alien atmospheric chemistry. Further predictions touch on planetary climates, weather systems, and geological activity. The interaction between deep oceans and volcanic or tectonic processes could facilitate nutrient recycling, essential for complex chemistry and potential biology. In some theoretical frameworks, ice layers created by immense pressures could insulate the internal oceans, influencing heat transfer and geochemical interactions. Importantly, ocean planets may exist over a wide range of orbital distances, including within the classical habitable zone of their stars, where conditions are optimal for liquid water as known on Earth. Yet, depending on atmospheric thickness and composition, ocean planets could maintain liquid water environments even beyond these traditional zones, extending the envelope within which life might exist. In terms of detectability, models predict certain atmospheric spectral signatures corresponding to abundant water vapor and possibly other volatiles like methane or ammonia. These signatures may be cloud-obscured or altered by photochemical processes, presenting challenges for astronomers, but also clear targets for advanced telescopes. The concept of ocean planets stretches beyond pure scientific curiosity into philosophical dimensions, inviting us to reconsider what constitutes a planet, a habitable environment, and even life itself. Such worlds test the limits of our Earth-centric perspective, pushing astronomers to develop more inclusive models that capture the magnificent variety of planetary conditions in our galaxy. Gliese 1214b stands as a prime example within this theoretical framework, a possible prototype of ocean planets, one whose observed properties tantalize us with the prospect of deep, exotic oceans and thick, mysterious atmospheres. As predictive models improve and observations become more precise, ocean planets promise to become a central focus in the pursuit of understanding the prevalence and nature of watery worlds that might be commonplace across the stars. The concept of water worlds has captured the human imagination for centuries, weaving its way through myths, literature, art, and ultimately science fiction, portraying alien planets entirely covered by vast oceans. These imaginative depictions evoke mesmerizing imagery: endless seas beneath unfamiliar skies, strange marine creatures thriving in deep alien waters, and distant horizons where water meets mysterious, perhaps uncharted atmospheres. Yet, as enchanting as these fictional portrayals are, the scientific reality of ocean planets, often called water worlds, reveals a far more complex and intriguing picture, with physical properties and environments that challenge our earthly intuitions. Science fiction often presents water worlds as paradisiacal or hostile settings, serving as backdrops for tales of exploration, colonization, or otherworldly adventures. Early to mid-20th century fiction, for example, sometimes imagined these worlds as temperate planets with Earth-like oceans and weather patterns. The water was presumed to be similar to terrestrial seawater, with familiar marine ecosystems thriving beneath placid surfaces. Other depictions explored extreme conditions, oceans under thick, cloudy atmospheres with crushing pressure or eternal storms raging across the globe. These visions ignited audiences' curiosity and inspired generations of scientists to consider alien oceanic environments as plausible and worth exploring. Yet, let us now consider how scientific inquiry contrasts with and enriches these portrayals. The first difference arises from a fundamental understanding of planetary formation and composition. Real ocean planets are not merely Earth-like spheres covered in water. Rather, they are often much larger, with depths and pressures far exceeding anything found on our planet. The gravitational forces on super-Earth-class ocean planets like Gliese, 12W, 14b, compress water and other volatiles into exotic states, such as high-pressure ices and supercritical fluids. This suggests oceans that are not shallow, sunlit seas but immense, deep layers where liquid and solid phases of water intermingle under extreme conditions. Furthermore, the composition of these oceans may differ substantially from that of Earth's. The chemistry may include a mix of water with ammonia, methane, or other volatiles, influenced by the planet's formation history and proximity to its star. In many ocean planet models, a thick atmosphere laden with water vapor and clouds of exotic chemistry envelops the world, sometimes obscuring direct observation of the surface entirely. This paints a picture of planets shrouded in haze and mist, rather than a clear, open ocean. Another difference comes from the understanding of planetary climates and atmospheric dynamics. Ocean worlds in reality might exhibit atmospheric pressures and temperatures far from the temperate or tropical Earth-like scenarios common in fiction. For instance, tidally locked planets, those that keep one face perpetually toward their star, can have permanent day and night sides, each with stark temperature contrasts that generate fierce winds and complex weather patterns unlike terrestrial norms. The chemical makeup of the atmosphere and the role of clouds or hazes can further diversify the environmental conditions in ways that science fiction is only beginning to explore comprehensively. Technological advances in observation provide yet more nuance. Data from telescopes such as Hubble and the upcoming James Webb Space Telescope show that atmospheric signatures of exoplanets, including candidate water worlds like Gliese, 12 and 14b, rarely match simplistic fictional ideals. Instead, atmospheric spectra often reveal flat or muted signals due to clouds, hazes, or complex molecular mixtures, challenging early expectations and demanding more sophisticated models. In addition, the timescales and evolutionary paths of ocean worlds introduce complexities often unaddressed in fiction. For example, whether water-rich planets retain their oceans over billions of years or lose them due to atmospheric escape processes depends heavily on stellar radiation, magnetic fields, and internal geology. Some ocean planets may evolve into worlds with thick, relentlessly hot atmospheres, while others may maintain subsurface oceans protected by ice layers. These scenarios imply a vibrant and varied class of worlds where water's role ranges from dominant surface feature to hidden internal reservoir. Nevertheless, the imaginative landscapes offered by science fiction retain immense value. They inspire questions about alien life, unique ecosystems, and the adaptations that might arise in water-dominated environments. Fiction often serves as a laboratory for exploring possibilities that pure scientific method has yet to fully apprehend. It also continuously feeds public interest, providing cultural momentum that supports scientific funding, discovery, and education. The synergy between science and fiction also fosters creative hypotheses about biochemistry, climate, and planetary processes. Could life exist in supercritical water oceans? How might atmospheric dynamics on these worlds drive cycles of chemicals needed for life? What forms of photosynthesis or chemosynthesis might flourish where sunlight patterns are unlike any on Earth? These questions push both arenas, scientific research and imaginative exploration, to evolve and converge. In closing, the real ocean planets and their depiction in science fiction form a captivating dialogue between our dreams and empirical knowledge. While science illuminates these worlds with hard data, refined models, and cautious optimism, fiction fills the spaces in between with wonder, speculation, and narrative depth. Together, they invite us to broaden our understanding of what it means to be a planet bathed in water, and to embrace the mysterious beauty of alien oceans stretching across our galaxy. Exploring the structure of Gliese 1214b invites us to peer beneath the veil of its mysterious atmosphere and clouds, attempting to visualize the intricate layers that compose this distant, enigmatic world. While direct observation remains out of reach, astronomers and planetary scientists construct models based on the planet's measured physical properties: mass, radius, density, and theoretical understanding of materials under extreme pressures and temperatures. The emerging picture reveals a world layered in complexity, where liquid, solid, and gaseous realms intertwine in an alien dance unlike anything found on Earth. At the very heart of Gliese 1214b likely lies a dense, rocky or metallic core, serving as the planet's foundational bedrock. This core may resemble Earth's interior in composition, primarily composed of iron, nickel, silicates, and other heavy elements, compressed under immense gravitational forces. Given the super-Earth's increased mass, about 6.5 times that of Earth, the pressures at this core could be extraordinarily high, causing materials to exhibit exotic phases and properties. Surrounding this dense core, the next substantial layer is hypothesized to be a vast mantle predominantly composed of high-pressure ices or supercritical fluids. These materials are not familiar ices that we encounter on Earth's surface, but are unique, dense phases of water and other volatile compounds that form only under tremendous pressure. For example, ice phases like Ice 7th and Ice X, crystalline structures stable at pressures millions of times those on Earth, could dominate this layer. This mantle might extend hundreds of kilometers outward, playing a pivotal role in the planet's heat transfer, magnetic field generation, and internal dynamics. Above this mantle, a thick global ocean may exist, composed of liquid water or a supercritical fluid, a state of matter that combines properties of gases and liquids. Unlike Earth's comparatively shallow and temperate oceans, the ocean on Gliese 1214b could be superheated and immense, enveloping the planet's entirety. This ocean would be a realm of great pressure and heat, where familiar notions of fluid dynamics and chemistry enter uncharted territory. The ocean's depth, potentially tens to hundreds of kilometers, challenges expectations rooted in terrestrial experience and suggests exotic seafloor conditions and chemical interactions. Capping this watery expanse is the planet's atmosphere, a shrouded layer that both reveals and conceals the planet's secrets. Observations indicate that Gliese 1214b likely possesses a thick atmosphere, possibly several hundred kilometers deep, rich in water vapor, hydrogen, and helium, or even more complex compounds, depending on the planet's formation and evolutionary history. Photochemical processes within this atmosphere may produce translucent or opaque clouds composed of unusual substances such as hydrocarbon hazes, high-altitude condensates, or dense water clouds that scatter and absorb incoming starlight. This atmospheric canopy profoundly influences the planet's surface conditions. It traps heat, regulates temperature gradients between the day and night sides of the tidally locked planet, and drives exotic weather patterns that might include acid rains, superheated storms, or dense fogs enveloping the planet in a perpetual mist. Models suggest these dynamics could affect the atmospheric circulation patterns and possibly even the chemistry of the underlying ocean, creating feedback loops that shape the long-term evolution of the planet. The boundaries between these layers are not rigid. Rather, they likely represent gradual transitions governed by the interplay of pressure, temperature, and chemical composition. For example, the interface between the supercritical ocean and the overlying atmosphere might be blurred, with continuous exchange of gases and energy. Similarly, interactions between the ice mantle and the rocky core could facilitate geochemical recycling, potentially influencing the availability of essential elements for prebiotic or even biological processes. Current models are still refining the estimated thickness of each layer and the precise material phases present, challenged by uncertainties in the planet's bulk composition and the complex physics of high-pressure water and gas mixtures. The degeneracy of possible solutions, where different internal combinations yield similar mass and radius, means that multiple structure scenarios remain plausible. Nevertheless, advances in observational astronomy reassure us that increasing data quality will improve constraints. The James Webb Space Telescope and upcoming missions aim to provide more detailed spectral data, which, when combined with precise physical measurements, will help discriminate among structural models by shedding light on atmospheric composition, cloud properties, and possibly surface conditions. In contemplating the layers beneath the clouds of Gliese 1214b, we envision a world that defies simple categorization. A planet where intense gravitation crafts exotic phases of water and rock, where the deep ocean might be a realm of supercritical fluid unknown on Earth, and where a thick veil of atmosphere both covers and protects this alien surface, simultaneously hiding and revealing its mysteries. These layers represent more than mere strata. They embody the profound complexity and diversity possible within the universe's planetary menagerie. Understanding Gliese 1214b's internal structure not only illuminates this specific world, but also informs our broader efforts to comprehend the nature of super-Earths and ocean planets as a class. It invites us to imagine alien environments where the familiar is transmuted into the extraordinary, expanding our scientific frontiers and our cosmic wonder. Venturing beneath the clouds of Gliese 1214b, we find ourselves immersed in a realm defined by extraordinary physical extremes, where pressures soar to unprecedented heights and temperatures reach formidable levels. These conditions present profound challenges for understanding alien oceanography, stretching the boundaries of terrestrial knowledge and inviting us to explore a landscape where familiar states of matter give way to exotic phenomena. At the heart of these challenges lies the planet's immense gravity, a direct consequence of its mass being over 6 times that of Earth, and its radius more than twice as large. This intensified gravity profoundly influences the pressure gradients within the planet's interior and along its potential ocean layers. Unlike Earth's oceans, which are limited to depths of about 11 kilometers within manageable pressure regimes, the water enveloping Gliese 1214b could extend hundreds of kilometers deep. Such depth implies pressures reaching hundreds of thousands to millions of times Earth's atmospheric pressure at sea level, conditions where water behaves in ways alien to our everyday experience. Under these staggering pressures, water transitions into a sequence of high-pressure ice phases, named ice phases, 7th, Fopi, and even beyond, each with distinct crystalline structures that defy normal ice's fragile geometry. These exotic ices are not fragile frozen surfaces, but are solid due to the intense squeeze from above, forming dense, hard mantles beneath the liquid layers. Far from the transparent, brittle ice we know, these high-pressure ices possess properties that influence heat conduction, chemical interactions, and internal dynamics. Further complicating this picture is the effect of temperature. Gliese 1214b resides close to an M-dwarf star, meaning that despite the star's modest overall luminosity, the planet experiences significant stellar heating. Surface and atmospheric temperatures on Gliese 1214b are estimated to range anywhere from about 400 to 600 Kelvin, roughly 127 to 327 degrees Celsius. These elevated temperatures, combined with crushing pressures, push water into a supercritical state, a phase where liquid and gas phases merge into a single fluid with extraordinary properties. Supercritical water oceans are a concept largely unfamiliar on Earth, but profoundly relevant in alien oceanography. In this state, water exhibits unique solvent capabilities, dissolving materials in ways distinct from ordinary liquid water and facilitating chemical reactions that could differ fundamentally from those in Earth's seas. This environment challenges conventional assumptions about ocean chemistry, nutrient cycles, and even the potential for supporting life. The intense pressures and temperatures also create steep environmental gradients. At the ocean's interface with the overlying atmosphere, pressures might be moderate enough to allow water vapor clouds and weather phenomena akin to storms and fog. Conversely, deeper layers rapidly transition to extreme conditions, possibly creating stratified ocean chemistry and layered convection cells that transport heat and chemicals throughout the ocean's depth. Such ultra-high-pressure environments prompt questions about geological and geochemical cycles within these planets. Pressures influence not only the physical states of materials, but also dictate phase changes in minerals and volatiles. For example, the interface between rocky mantle and ocean could generate unique chemical reactions, potentially recycling elements essential for prebiotic chemistry or sustaining geologic activity that replenishes the ocean with nutrients. Modeling these conditions is a formidable task. Terrestrial laboratories can simulate high pressures and temperatures, but reproducing the simultaneous extremes found in Gliese 1214b's interior remains challenging. Scientists rely heavily on theoretical computations, experimental proxies, and extrapolations from known physics, but uncertainties linger. Equations of state describing water's behavior under supercritical conditions, for example, remain an active area of research. Furthermore, understanding how such environments affect atmospheric escape processes is critical. Planetary atmospheres under intense stellar irradiation may lose mass over time, and supercritical oceans also influence volatile exchanges with the atmosphere. These dynamics shape planetary evolution and long-term habitability prospects. Despite these challenges, studying alien oceanography under extreme pressures and temperatures offers promising insights. It stretches disciplines from planetary science to chemistry and biology, pushing us to consider life's adaptability in environments far removed from Earth's gentle seas. Could exotic chemistries in such high-pressure oceans sustain forms of life relying on novel biochemical pathways? Might life exploit supercritical water's solvent properties in ways completely alien to terrestrial biology? Gliese 1214b, positioned as a prototype ocean planet, invites us to ponder these deep mysteries. Its extreme pressures and temperatures turn oceanography into an exploration of the extraordinary, where water's phases and behaviors transcend terrestrial norms and open windows into new scientific vistas. Conquering these challenges demands advances in observational astronomy, laboratory physics, and theoretical modeling, a multidisciplinary quest to understand the nature of alien waters shaping these mysterious, distant worlds. As we continue our journey, appreciating the extreme pressure and temperature regimes of Gliese 1214b prepares us to delve into the intriguing results of atmospheric studies, which seek to detect water vapor and other indicators in this planet's thick envelope, revealing fragments of the puzzle about its oceanic and atmospheric secrets. The study of Gliese 1214b's atmosphere represents a pivotal step in unraveling the mysteries of this intriguing super-Earth, especially because its proximity and orbit make it one of the most accessible exoplanets for atmospheric characterization. Among the most powerful instruments used to probe this alien world's atmosphere has been the Hubble Space Telescope, whose observations have opened a window, albeit somewhat hazy, into the composition and dynamics of Gliese 1214b's gaseous envelope. Central to these efforts is the search for water vapor, a critical marker that may hint at the planet's putative oceanic nature and shape our understanding of its climate and potential habitability. The methodology employed in atmospheric studies like those conducted by Hubble relies primarily on transit spectroscopy. When Gliese 1214b passes in front of its host star, a small fraction of the starlight filters through the planet's upper atmosphere before reaching our telescopes. Different molecules absorb light at specific wavelengths, imprinting distinct absorption features on the starlight's spectrum. By carefully analyzing these spectral fingerprints, astronomers attempt to identify the constituent gases, such as water vapor, methane, carbon dioxide, or hydrogen. Initial observations of Gliese 1214b's transits with Hubble's Wide Field Camera 3 were met with both excitement and frustration. The data did not reveal the expected strong water absorption features anticipated from a planet hypothesized to be rich in water vapor. Instead, the spectrum appeared remarkably flat and featureless over the near-infrared wavelengths observed. This unexpected outcome suggested the presence of thick clouds or hazes obscuring the deeper atmospheric layers, effectively muting the signatures of molecules that might otherwise be discernible. One interpretation of these results is that the atmosphere of Gliese 1214b might be enveloped in high-altitude clouds composed of enigmatic substances, such as photochemically produced hydrocarbon hazes or clouds of saline particles. These potential cloud decks would scatter and absorb light uniformly across a range of wavelengths, creating the observed flat spectra. The nature and composition of these clouds remain topics of active research, as understanding them is crucial for refining models of atmospheric chemistry and thermal structure. Despite the challenge posed by hazes and clouds, subsequent observations have provided incremental information. The absence of strong spectral features rules out clear, hydrogen-dominated atmospheres unbeclouded by aerosols, guiding scientists toward models that include either thick, high molecular weight atmospheres or obscuring aerosols. These possibilities influence theories about the planet's origin, evolution, and atmospheric retention. Simultaneously, other molecules beyond water vapor have been of interest, such as methane and carbon dioxide, which play essential roles in greenhouse effects and photochemical cycles. While direct detection remains elusive, their potential presence adds complexity to the atmospheric puzzle and hints at dynamic chemical interactions. Ground-based telescopes complement Hubble's space-based observations by performing high-resolution spectroscopy, seeking to detect planetary signals in the visible and infrared bands amid stellar noise. These efforts, though technically demanding, contribute valuable constraints and cross-validation of atmospheric characteristics. Crucially, the limitations encountered with current technology, especially the masking effects of clouds and hazes, have framed future plans and ambitions. The upcoming James Webb Space Telescope, JWST, with its broader wavelength coverage and greater sensitivity, is poised to revolutionize atmospheric studies of Gliese 1214b. JWST's ability to probe mid-infrared regions is expected to penetrate or circumvent cloud layers, potentially unveiling spectral features hitherto hidden from view and providing definitive insights into atmospheric composition, temperature profiles, and pressure conditions. Beyond the detection of water vapor itself, these atmospheric studies also provide clues about the planet's climate dynamics, like temperature gradients between the permanent day and night sides, vertical atmospheric mixing, and the presence of exotic weather systems. Such data enrich our understanding of the complex interactions between atmosphere, potential ocean layers, and stellar radiation. Studying Gliese, 1214b's atmosphere with Hubble has thus been a dance between hope and complexity, a scientific journey marked by gradual progress, unexpected challenges, and evolving methodologies. It exemplifies the broader endeavor of exoplanetary science, where each observation refines our models and expands our appreciation of planetary diversity. This endeavor showcases the power of remote sensing techniques, high-precision spectroscopy, and space-based observatories in transcending vast cosmic distances to study the atmospheres of super-Earths. In combination with theoretical models, such observations deepen the narrative of Gliese 1214b as a potential ocean planet enveloped in an alien atmosphere, its spectral whispers among the stars beckoning us to learn more about these faraway watery worlds and their place in the grand tapestry of the cosmos. Spectral analysis stands as one of the most powerful investigative tools astrophysicists use to unravel the chemical compositions and physical conditions of distant exoplanets like Gliese 1214IB. This method allows scientists to decode the planet's atmospheric secrets by examining the way molecules absorb and emit light over various wavelengths, essentially interpreting the unique chemical fingerprints that different substances imprint on starlight filtered through or reflected by an exoplanet's atmosphere. At the core of spectral analysis is the principle that every molecule interacts with electromagnetic radiation in a characteristic way. When starlight passes through Gliese 1214b's atmosphere during transit, or when the planet emits its own thermal radiation, atmospheric gases absorb photons at specific wavelengths corresponding to transitions between molecular energy levels. These absorption or emission lines form a spectrum, a detailed barcode, from which researchers infer the presence and abundance of molecules such as water vapor, methane, carbon dioxide, or hydrogen. For Gliese 1214b, spectral signatures have been sought primarily through transit spectroscopy. As the planet crosses its host star's disk, a minuscule portion of the starlight filters through the outer atmosphere. Instruments sensitive to minute spectral variations capture these changes, yielding spectra that can then be analyzed. However, the task is fraught with subtleties. The thickness and composition of the atmosphere, the presence of clouds or hazes, and instrumental precision all affect the clarity and shape of the absorption features. Early spectral studies of Gliese 1214b revealed puzzling results. Contrary to expectations that water vapor would be a dominant and detectable component, observations yielded an unusually flat spectrum across infrared wavelengths. The absence of prominent absorption features indicated either a featureless or heavily muted atmosphere, potentially due to high-altitude clouds or haze layers that scatter and absorb broadly, obscuring molecular fingerprints beneath. This finding shifted the conversation about the planet's atmospheric and surface conditions, suggesting a more complex, layered environment than a clear, hydrogen-rich atmosphere. Researchers then employed sophisticated models incorporating various compositions and cloud properties to explain the flat spectrum. High molecular weight atmospheres composed of water vapor, nitrogen, or carbon dioxide could naturally produce flatter spectra, as could thick aerosols formed through photochemical reactions stimulated by stellar ultraviolet radiation. Experimental simulations and atmospheric chemistry models attempt to reproduce these phenomena, helping to interpret the ambiguous spectral data. Beyond water, scientists are also vigilantly searching for methane, a molecule of significant astrobiological interest, as well as carbon dioxide and ammonia. Their spectroscopic signatures, if present, can reveal clues about atmospheric processes, photochemistry, and potential habitability. Yet, like water vapor, these signatures can be masked by clouds or confused by overlapping molecular bands, complicating interpretation. High-resolution spectroscopy from advanced ground-based telescopes complements space-based measurements by attempting to resolve finer spectral details against the background noise of the star and Earth's atmosphere. Techniques like cross-correlation spectroscopy have proven effective in detecting molecular species in exoplanetary atmospheres, though applying them to a relatively faint M-dwarf system orbiting at 48 light-years remains challenging. The interpretation of spectral fingerprints also depends on understanding the temperature and pressure profiles within Gliese 1214b's atmosphere. Absorption features, shapes, and depths vary not only by molecular concentration, but also by the atmospheric temperature gradient and the vertical mixing of gases. Coupled radiative transfer and atmospheric circulation models allow researchers to simulate how photons traverse various atmospheric layers, refining interpretation of the spectra. In addition to discerning chemical composition, spectral analysis informs on cloud particle sizes and distributions, atmospheric scale heights, and potential photochemical hazes. These properties influence the planet's albedo, the amount of starlight reflected, and the greenhouse effect, which in turn affects surface or ocean temperatures, crucial for assessing potential habitability. As instrumental capabilities improve, especially with the advent of the James Webb Space Telescope and upcoming extremely large telescopes on Earth, the spectral analysis of Gliese 1214b promises to gain unprecedented resolution and wavelength coverage. Observations extending into mid-infrared wavelengths will probe deeper atmospheric layers and potentially cut through clouds or hazes that currently obscure vital information. Overall, interpreting the chemical fingerprints in Gliese 1214b's spectra is a subtle and evolving science, melding observational data, laboratory spectroscopy, theoretical modeling, and innovative analytic techniques. This detective work gradually transforms faint, distant light into comprehensive knowledge about the planetary atmosphere, surface conditions, and by extension, this remarkable ocean planet's place in the mosaic of worlds beyond our solar system. Modeling the atmospheres of alien worlds like Gliese 1214b presents a rich tapestry of scientific challenges, weaving together elements of physics, chemistry, and planetary science in a complex endeavor rife with uncertainties and surprises. Unlike Earth's atmosphere, whose properties are well studied and predictable, the atmospheres of distant exoplanets inhabit realms of unfamiliar temperature, pressure, and composition, often far beyond human experience. Understanding these exotic envelopes requires constructing theoretical frameworks that can accommodate extreme environments, limited observational data, and diverse planetary histories. One of the primary challenges centers on the fundamental lack of direct information. For distant exoplanets such as Gliese 1214b, astronomers rely largely on indirect measurements, transit light curves, spectra, and mass radius determinations, to infer atmospheric properties. These datasets are often sparse, noisy, and can be ambiguous due to degeneracies in interpretation. For instance, a flat transmission spectrum might indicate either a high-altitude cloud deck obscuring absorption features or an atmosphere composed of heavy molecules with intrinsically muted spectral signatures. Disentangling such scenarios requires sophisticated modeling. Another substantial hurdle arises from the extreme and unfamiliar physical conditions under which these atmospheres exist. Pressures within Gliese 1214b's atmosphere may range from near vacuum at high altitudes to thousands or millions of atmospheres near the surface or below cloud layers. Temperatures vary dramatically, influenced by its tidally locked orbit and proximity to its cool red dwarf star, creating strong thermal gradients between day and night sides. Accurately simulating these regimes demands comprehensive radiative transfer calculations that include absorption, emission, and scattering across a vast spectrum of wavelengths, accounting for complex interactions among molecules, aerosols, and clouds. Chemical complexity compounds the modeling challenge. Atmospheric compositions may include not only familiar species such as water vapor, methane, and carbon dioxide, but potentially exotic compounds formed through photochemistry and thermochemistry unique to the planet's environment. Reactions driven by stellar ultraviolet radiation can produce hazes analogous to those on Titan, or create molecular species not common on Earth, influencing both the climate and observable spectral features. Modeling these chemical networks requires extensive laboratory data and theoretical inputs, which are often incomplete or uncertain for such exotic conditions. Furthermore, cloud and haze formation represent formidable obstacles. Clouds strongly influence atmospheric opacity, the greenhouse effect, and spectral signatures, but depend on poorly constrained microphysical processes such as particle nucleation, growth, and sedimentation under alien chemistries and atmospheric dynamics. The challenge is especially acute for Gliese 1214b, whose observed flat spectra strongly hint at thick, high-altitude clouds or hazes masking absorption features. Integrating cloud models into atmospheric simulations demands multidimensional treatments that couple microphysics with global circulation models, stretching computational limits. Dynamical modeling introduces additional complexity. Tidally locked planets feature permanent day and night hemispheres, inducing atmospheric circulation patterns that redistribute heat and chemicals across hemispheres in ways very different from Earth's diurnal cycles. Simulating these flows requires three-dimensional general circulation models, GCMs, that incorporate radiation, chemistry, and cloud feedbacks. Intricate simulations that demand significant computational resources and parameter tuning. Another challenge lies in addressing the wide parameter space. Variations in stellar radiation intensity, planetary mass, surface gravity, elemental abundances, and initial atmospheric inventories lead to a plethora of plausible atmospheric states. Modeling endeavors must therefore explore a broad range of scenarios to define possible atmospheric structures and compositions consistent with observational constraints. Uncertainties in fundamental data, such as molecular opacities at high pressures and temperatures or reaction rate coefficients, further complicate the modeling effort. These data gaps necessitate approximations that introduce degeneracies and ambiguities. Laboratory experiments and quantum chemical calculations strive to fill these gaps, but cannot yet cover all relevant species and conditions. Despite these obstacles, advances in computing power, observational techniques, and interdisciplinary collaboration continue to propel atmospheric modeling forward. Iterative comparisons between model predictions and observations refine our understanding, progressively narrowing the range of viable atmospheric compositions and structures. The imminent launch and operation of next-generation telescopes, like the James Webb Space Telescope, promise richer datasets that will stimulate more sophisticated models. In summary, the challenges of modeling alien atmospheres such as Gliese 1214b's lie in limited data, extreme and unfamiliar physical conditions, complex chemistry, cloud and haze microphysics, dynamical atmospheric circulation, and gaps in fundamental molecular data. Overcoming these challenges not only advances exoplanetary science, but also expands the horizons of atmospheric physics, chemistry, and astrobiology, revealing the astonishing diversity of worlds populating our galaxy and refining our quest to understand planets that may resemble, and yet differ profoundly from, our own blue planet. Gliese 1214b occupies a special place in the evolving landscape of exoplanet research, emerging as one of the most scrutinized candidates among a growing catalog of so-called ocean planets or water worlds. To appreciate its significance and to grasp the broader context of such exotic worlds, it is essential to compare Gliese 1214b with other known or hypothesized ocean planets, examining similarities and differences in their properties, environments, and potential for harboring oceans beneath alien skies. Ocean planets, by definition, are characterized by substantial quantities of water or other volatiles forming global oceans that may span the entire planetary surface, a feature setting them apart from planets with fragmented seas and continents like Earth. Early speculative models posited ocean worlds as a plausible intermediate category between rocky terrestrial planets and gaseous giants, and recent discoveries have lent weight to these models by revealing planets whose densities suggest significant volatile content. Starting with Gliese 1214b, its size and mass, approximately 2.6 Earth radii and 6.5 Earth masses, indicate a super-Earth or mini-Neptune classification with a low density implying a large fraction of water or a thick gaseous envelope. Its orbit around a relatively quiet red dwarf star and the proximity allowing detailed study have made it a cornerstone in the ocean planet discourse. Comparing Gliese 1214b to Kepler 62a and Kepler 62f, two other intriguing ocean planet candidates, offers valuable insights. Both Kepler 62m and Anaquitidu F reside in the habitable zone of their host star, a K-type dwarf, placing them at distances where liquid water could be stable on their surfaces under suitable atmospheric conditions. These planets are somewhat smaller than Gliese 1214b, Kepler 62y, measuring about 1.6 Earth radii, and Kepler 62f, roughly 1.4 Earth radii. Their lower masses and sizes suggest thinner atmospheres and potentially more Earth-like compositions, albeit with higher water fractions than Earth. Unlike Gliese 1214b, their greater orbital distances may afford cooler surface temperatures, possibly conducive to liquid water oceans, depending on atmospheric properties. Moving to larger candidates, planets such as K2-18b further expand the diversity of ocean world possibilities. K2-18b, nearly 8 times the mass of Earth and about 2.6 Earth radii, resembles Gliese 1214b in size, but orbits a red dwarf star within the habitable zone, where conditions may allow liquid water at the surface. Notably, recent observations have indicated the presence of water vapor in its atmosphere, marking an exciting development for the field. In comparison, Gliese 1214b presents a warmer environment due to its tight orbit, challenging assumptions about surface liquid water, but reinforcing the need to consider exotic oceanic and atmospheric states. Another comparison can be drawn with planets like TRAPPIST-1e, one of 7 Earth-sized planets orbiting a cooler red dwarf star. TRAPPIST-1e, slightly smaller than Earth, lies within its star's habitable zone and is a compelling candidate for surface or subsurface oceans. Though smaller than Gliese 1214b, the TRAPPIST-1 system underscores the variety of planetary architectures that might host water environments, ranging from super-Earths down to Earth-sized or smaller worlds. Diversity among ocean planet candidates also manifests in atmospheric composition and observational accessibility. Planets like Gliese 1214b and K2-2.18b orbit relatively bright nearby stars that enhance the quality of atmospheric data through transit spectroscopy, while others are more distant or around faint stars, limiting current observational capabilities. This factor influences how confidently scientists can characterize their atmospheres and infer the ocean existence. Even among confirmed planets with similar bulk properties, differences in stellar radiation, magnetic activity, and planetary history induce distinct environmental conditions, altering atmospheric retention, chemistry, and potentially crust or ocean interactions. For instance, Gliese 1214b receives higher stellar flux due to its close orbit, resulting in hotter equilibrium temperatures, while more distant ocean planet candidates might have cooler climates, enabling different oceanic and atmospheric chemistries. Importantly, comparative studies highlight how variations in planet formation and migration histories shape water content and distribution. Some ocean planets may have formed beyond the snowline and migrated inward, preserving large volatile inventories, while others formed in situ with limited water accretion. These differing evolutions offer rich fields of inquiry into planetary system development and water delivery mechanisms. While direct imaging and detailed surface characterization remain beyond current capabilities for these distant worlds, the comparative approach leverages mass, radius, density, orbital parameters, and atmospheric data to sketch their probable states and evolutionary trajectories. This comparative exoplanetology enriches our theoretical frameworks and informs target selection for future observational campaigns designed to probe ocean planets more deeply. In sum, Gliese 1214b serves as a vital reference point among known ocean planet candidates, sharing key characteristics and environmental challenges with some, yet differing markedly in orbital proximity and atmospheric conditions from others. Together, these worlds represent a continuum of possibilities, from mini-Neptunes with substantial atmospheres to potentially habitable water-rich planets, forming a compelling mosaic that continues to expand our understanding of planetary diversity and the cosmic prevalence of watery realms. Exploring the potential weather systems on Gliese 1214b invites us into a realm where atmospheric physics transcends terrestrial familiarity, giving rise to phenomena that are both exotic and captivating. The planet's unique combination of proximity to its cool red dwarf star, its possible composition as an ocean planet, and its dense, obscuring atmosphere set the stage for meteorological dynamics that challenge our conventional understanding of weather. Rain, fog, and storms on Gliese 1214b would not only be shaped by its stark environmental contrasts, but could manifest in forms and intensities unlike anything experienced on Earth. At the core of this atmospheric complexity is the planet's tidally locked nature. One hemisphere faces the star perpetually, enduring constant daylight and intense stellar irradiation, while the opposite side remains in continuous darkness and cold. This asymmetry establishes steep temperature gradients across the planet, driving powerful winds and heat transfer through the atmosphere. These winds likely swirl in vast planet-encompassing jet streams, transporting heat from the scorching day side to the frigid night side. Such flows can give rise to dynamic weather systems, including vast cloud formations and precipitation. Rain on Gliese 1214b, if it occurs, would differ radically from Earth's water cycle. Given the planet's elevated atmospheric pressures and temperatures, condensed materials could extend beyond familiar water droplets. Atmospheric constituents might include superheated steam or exotic condensates, such as hydrocarbons or mineral vapors precipitating as liquid or solid rain. These rains might fall in intense downpours on the day side or form on the twilight terminator, where temperatures are moderate, cycling materials between atmospheric layers and surface or oceanic reservoirs. Fog and mist are likely common on Gliese 1214b due to its thick atmosphere and substantial cloud cover. Such fog could envelop large portions of the planet, composed of finely suspended droplets or particles formed through photochemical reactions initiated by the star's radiation. This atmospheric haze would limit visibility and influence the planet's thermal balance, by reflecting and absorbing stellar and planetary radiation. Given the permanent day or night hemispheres, fog could persist indefinitely in certain regions, creating alien landscapes of perpetual mist. Superheated storms represent a particularly intriguing possibility. On the hot day side, temperatures may reach several hundred degrees Celsius, elevating vapor pressures and driving vigorous convection. These conditions can fuel towering cloud systems and violent windstorms, perhaps more intense than any terrestrial hurricane. The storms could carry charged particles, produce lightning, and generate complex chemical reactions within the atmosphere, dynamically shaping the planet's climate and atmospheric chemistry. Additionally, the interaction of stellar winds from the red dwarf star with Gliese 1214b's atmosphere might provoke auroral phenomena or magnetospheric disturbances that further energize weather systems. If the planet lacks a strong magnetic field, atmospheric erosion or direct particle interactions could create layers of charged particles, contributing to complex atmospheric dynamics and transient weather phenomena. Cloud compositions on Gliese 1214b are expected to be diverse, potentially including water clouds, but also clouds of ammonia, methane, or even exotic salts and hydrocarbons, depending on atmospheric chemistry and temperature pressure regimes. These clouds can form intricate layers that evolve over time, influencing albedo and potentially masking deeper atmospheric features from observational instruments. Modeling these weather systems poses significant challenges. Simulations must integrate radiative transfer, cloud microphysics, atmospheric chemistry, and global circulation models tailored to the unusual environmental parameters of Gliese 1214b. Understanding how these processes interact on different hemispheres, their transient behaviors, and spatial variability remains an active area of research. In effect, Gliese 1214b's weather can be envisaged as a symphony of extremes: unending twilight mists, torrential rains of strange composition, and superheated, raging storms sweeping across the dayside, all fueled by the planet's intimate relationship with its star and its own peculiar atmospheric makeup. These meteorological phenomena not only shape the planet's present environment, but also influence its long-term evolution, atmospheric retention, and potential habitability. As observational technology advances, future telescopes like the James Webb Space Telescope will seek signatures of such dynamic weather by examining time-variable spectra or monitoring brightness fluctuations, aiming to detect clouds, storms, or global circulation patterns. Ultimately, contemplating the exotic weather on Gliese 1214b expands our horizons beyond Earth's familiar skies, inviting us to imagine a planet where rain falls not as gentle showers, but as alien torrents, where fog persists as a spectral shroud, and where storms roar with a ferocity born from conditions both harsh and wondrous, underscoring the diverse and dynamic nature of worlds beyond our own. The tantalizing question of whether Gliese 1214b harbors the conditions necessary to support life moves us to the forefront of astrobiological inquiry, an interdisciplinary field dedicated to understanding the origins, evolution, and distribution of life in the universe. Assessing the habitability of this exotic exoplanet requires careful consideration of a complex interplay of factors, from its physical environment and chemical composition to the impact of stellar radiation and planetary dynamics, each influencing the potential emergence and sustainability of life. At the foundation of life as we know it lies liquid water, a solvent essential for biochemical reactions and cellular processes. Gliese 1214b's classification as a potential ocean planet makes it an intriguing candidate. Its low density and size suggest the presence of significant water content, possibly in vast, global oceans. However, the sheer scale, pressure, and temperature of these oceans on Gliese 1214 BOI likely eclipse earthly norms. Pressures reaching millions of atmospheres and elevated temperatures, perhaps between 400 to 600 Kelvin, raise questions about the fluid state of water and whether it exists as a supercritical fluid rather than simple liquid. While such a medium is considerably different from Earth's oceans, it remains an open scientific question whether prebiotic chemistry or even life could arise under such conditions. The atmospheric composition and structure are similarly critical. An atmosphere dense with hydrogen, helium, or other gases could exert strong greenhouse effects, influencing surface temperature, pressure, and photochemistry. The possible presence of thick clouds or hazes could limit stellar radiation penetration, which on one hand might protect potential life forms from harmful ultraviolet or particle radiation, but on the other might restrict energy available for photosynthesis or other energy harvesting processes. The energetic environment created by its red dwarf host star poses additional challenges. While red dwarfs tend to be cooler, many exhibit powerful flares and high levels of X-ray or ultraviolet emissions during their youth, which could strip atmospheres or damage nascent life. An aspect of particular astrobiological interest lies in the planet's tidal locking, a permanent day side facing the star and a perpetual night side in darkness. This configuration prompts questions about the planet's climate stability and habitability niches. Some models suggest that atmospheric circulation could redistribute heat effectively, tempering extremes and creating temperate regions near the terminator, the boundary between day and night, that could harbor conditions more conducive to life. These zones may sustain complex climate systems where liquid water is stable, and where energy gradients could drive biochemical cycles. Geological activity, driven perhaps by tidal heating from the star's gravitational pull, could supply the necessary chemical disequilibria believed essential for life. On Earth, hydrothermal vents at ocean floors are hot spots of biological activity, providing nutrients and energy to support diverse ecosystems independent of sunlight. If similar internal heating exists on Gliese 1214b, it could foster subsurface habitats insulated from surface extremes, expanding potential refuges where life might arise or persist. Nevertheless, there remain significant uncertainties. High pressures may inhibit complex biological molecules' formation or stability. Exotic chemistries might dominate, potentially leading to life forms unfamiliar to terrestrial biology, or conversely preclude life altogether. A heavy hydrogen atmosphere might suppress surface habitability by creating a barrier to energy transfer or fostering uninhabitable chemical conditions. Current observational capabilities cannot directly detect biosignatures, chemical markers indicative of life, in Gliese 1214b's atmosphere, but future missions like the James Webb Space Telescope and subsequent advanced observatories may provide critical insights. By probing atmospheric composition for molecules such as oxygen, ozone, methane, or complex organics in disequilibrium, a hallmark of biological activity, astronomers aim to test the planet's habitability and even the possible presence of life. Ultimately, the astrobiological potential of Gliese 1214b embodies both the promise and complexity inherent in the search for life beyond Earth. It challenges us to expand our understanding of habitability beyond Earth-centric paradigms, considering that life elsewhere may arise under conditions profoundly different, yet no less wondrous. As we continue to investigate this ocean planet, the quest to determine whether it harbors life remains a compelling thread weaving together astronomy, planetary science, chemistry, and biology. A thread that brings us closer to answering some of humanity's most profound questions about our place in the cosmos. When contemplating the habitability of Gliese 1214b, it is essential to assess a suite of environmental and astrophysical factors, chief among them tidal forces, radiation exposure, and magnetic field presence, that collectively shape the potential for this distant ocean world to sustain or support life. While we often envision habitability in terms of temperature and liquid water alone, these additional factors profoundly influence atmospheric retention, surface conditions, and biological viability in ways that are critical, yet far from straightforward, especially for planets orbiting red dwarf stars like Gliese 1214. Tidal forces exerted on Gliese 1214b are expected to be significant due to its extremely close orbit around its host star, completing a revolution roughly every 1.58 Earth days. This intimate stellar embrace results in intense gravitational interaction, which likely locks the planet tidally so that one hemisphere perpetually faces the star, while the other remains in constant darkness. This synchronous rotation creates stark climatic dichotomies, eternal day and eternal night, that demand complex atmospheric and oceanographic energy redistribution to moderate extreme temperatures. In addition, tidal flexing deforms the planet's interior, generating internal frictional heating. This tidal heating can sustain geological activity such as volcanism or tectonics, potentially driving chemical cycling crucial for maintaining habitability by resurfacing minerals and fostering nutrient recycling akin to Earth's hydrothermal vent ecosystems. However, tidal locking also raises challenges. The persistent day side may experience intense heating and atmospheric evaporation, while the night side may plunge into deep freezes, potentially causing atmospheric constituents to condense and precipitate out, leading to atmospheric collapse scenarios. The effectiveness of heat and atmospheric circulation in mitigating these effects is critical. A robust atmosphere and dynamic climate are vital for tempering such extremes to maintain liquid water environments. Radiation environment is another pivotal consideration. M-dwarf stars like Gliese 1214 tend to exhibit heightened magnetic activity, especially in earlier evolutionary stages, producing powerful flares that emit bursts of ultraviolet and X-ray radiation. Such high-energy irradiation can erode planetary atmospheres through processes like photoevaporation and sputtering. For Gliese 1214b, the proximity to its star exacerbates exposure to this harmful radiation. This can strip lighter atmospheric components, alter atmospheric chemistry by driving photochemical reactions, and increase surface radiation levels to biologically damaging intensities. Yet, mature red dwarfs often calm over time, and Gliese 1214 appears to be relatively quiet compared to more active red dwarfs. Nevertheless, even infrequent but intense flare events remain a hazard to atmosphere integrity and potential life. The planet's atmosphere may also possess protective layers, such as thick cloud decks or high-altitude hazes, that absorb or scatter harmful radiation, providing additional shielding. Understanding the balance between atmospheric erosion and replenishment over geological timescales is fundamental to evaluating habitability. Magnetic fields are a critical safeguard against stellar radiation and charged particle bombardment. On Earth, the geomagnetic field protects the atmosphere and biosphere, deflecting solar wind and cosmic rays. For Gliese 1214b, the presence and strength of a magnetic field remain unknown but crucial. A strong magnetosphere would mitigate atmospheric loss and preserve surface conditions conducive to life. In contrast, a weak or absent magnetic field could leave the atmosphere vulnerable to erosion, diminishing habitability prospects. The generation of a magnetic field depends on the planet's internal dynamics, such as a liquid, convecting metallic core, producing a dynamo effect. Tidal heating may influence this dynamo by affecting convection strength and core temperature. However, elevated planetary mass and pressure conditions could alter the internal structure and dynamics in ways that either support or suppress magnetic field generation, adding complexity to predictions. Collectively, tidal forces, radiation exposure, and magnetic fields weave a nuanced portrait of Gliese 1214b's habitability landscape. The potent tidal interactions may energize internal processes favorable for sustaining life-essential geochemical cycles, but create climatic extremes requiring atmospheric or oceanic heat redistribution. The radiation environment poses threats that could degrade atmospheres and damage potential life, but might be mitigated by atmospheric shielding and magnetic protection that are still subject to active investigation. Synthesizing these factors, current astrobiological models suggest that while Gliese 1214b faces formidable challenges to habitability, especially given its tight orbit and stellar environment, pockets of stable conditions may exist, particularly near the day-night terminator or beneath atmospheric layers, where life could potentially establish. Future observations targeting magnetic field signatures, atmospheric composition, and stellar activity patterns, combined with advanced modeling, will be essential to paint a more definitive picture. Thus, understanding the interplay of tidal forces, stellar radiation, and planetary magnetism unveils critical dimensions of Gliese 1214b's habitability, illustrating the complexity of evaluating life's potential on distant ocean worlds and advancing our broader quest to grasp life's cosmic prevalence. As our exploration of Gliese 1214b advances, the horizon of future observations shines brightly with the promise of revolutionary breakthroughs, especially with the James Webb Space Telescope, JWST, poised to transform our understanding of this enigmatic ocean world. JWST, equipped with unprecedented sensitivity and spectral range, represents the next-generation observatory designed to penetrate the complexities of distant exoplanet atmospheres and surface conditions that have eluded our grasp so far. The James Webb Space Telescope's capabilities are tailor-made for studying planets like Gliese 1214b. Its instruments cover a broad range of infrared wavelengths, enabling the detection of molecular signatures even when obscured by clouds or hazes. Unlike its predecessor, Hubble, which struggled to identify clear spectral features, JWST's superior light-gathering ability and spectral resolution offer a profound improvement. Scientists anticipate that JWST will distinguish between thick hydrogen-rich atmospheres, water-dominated envelopes, and dense cloud layers, a feat critical to resolving whether Gliese 1214b is truly an ocean planet or possesses a different atmospheric composition. In particular, JWST observations will focus on refined transit spectroscopy, measuring how starlight filters through the atmosphere with exquisite precision. This will provide tighter constraints on water vapor, methane, carbon dioxide, and potential biosignature gases. Moreover, secondary eclipse measurements, the brief fading of planetary light when it moves behind its star, will inform temperature and energy balance, revealing how heat redistributes across this tidally locked world. Beyond JWST, upcoming facilities such as the Extremely Large Telescope, ELT, and other ground-based observatories equipped with cutting-edge adaptive optics and spectrographs will complement space observations. These telescopes will pursue high-dispersion spectroscopy to detect atmospheric dynamics like winds and rotation speeds, and to search for transient weather phenomena. Multi-wavelength campaigns combining space and ground data promise a holistic picture of Gliese 1214b's atmospheric processes. Looking further ahead, proposed missions like the Large UV Optical Tjaktich Infrared Surveyor, LUVOIR, or Habitable Exoplanet Observatory, WARS-HABEX, envision direct imaging capabilities able to isolate exoplanet light from their stars, potentially imaging surface features or atmospheric layers. While such missions are still conceptual, their realization would mark a paradigm shift, allowing us to observe ocean planets with unprecedented clarity. Technological innovations in detector sensitivity, coronagraphs, and starshade designs are critical drivers for these future missions, aimed at pushing the boundaries of what can be seen across tens of light years. Additionally, advances in data analysis, machine learning, and atmospheric retrieval algorithms will enhance our ability to interpret subtle signals embedded in starlight. Collectively, the synergy of JWST and future observatories will enable a multidimensional approach to studying Gliese 1214b, delving into its atmospheric chemistry, climate, potential cloud dynamics, and even signatures indicative of ocean presence. These observations promise to refine or refute existing models, opening windows into planetary formation, evolution, and the conditions conducive to life beyond our solar system. In this exciting era, every new observation acts as a stepping stone deeper into the mysteries of ocean planets. Gliese 1214b, once a faint dot of light exhibiting periodic dimming, now stands at the forefront of our quest to understand watery worlds in alien star systems. As JWST lifts the veil and beyond, our journey continues, expanding the frontier of knowledge and drawing us ever closer to answering humanity's enduring question: are we alone in the universe? As our understanding of Gliese 1214b deepens, it serves as a catalyst for the broader, more ambitious pursuit of ocean planets scattered throughout our Milky Way galaxy. This expanding search reflects an extraordinary cosmic exploration drive, fueled by numerous exoplanet discoveries, revealing that planets with substantial water content may be common rather than exceptional. Unveiling the population, characteristics, and distribution of ocean worlds across the galaxy is critical for understanding planetary diversity, chemical evolution, and the potential prevalence of life beyond Earth. The Milky Way, our galactic home, is a vast spiral galaxy housing hundreds of billions of stars, many accompanied by planetary systems. Surveys by space telescopes like Kepler, TESS, and ground-based observatories have uncovered thousands of exoplanets with sizes and densities suggestive of water-rich compositions, ranging from small, rocky planets to larger super-Earths and mini-Neptunes. These findings hint that planets with deep global oceans or thick volatile envelopes are not mere curiosities, but may represent a significant fraction of all planets. Statistical analyses of exoplanet populations indicate that planets between one and several Earth masses, categories where ocean planets are most likely to occur, are more common than gas giants or even Earth-sized rocky worlds. Moreover, the existence of so-called sub-Neptunes, characterized by low densities consistent with substantial volatile layers, reinforces the expectation that many ocean planets inhabit the galaxy, particularly around smaller stars like red dwarfs, which dominate stellar demographics. The diversity of stellar types and planetary formation pathways suggests ocean planets could vary widely in composition, temperature, atmospheric properties, and evolutionary history. Some may orbit close to their stars, like Gliese 1214b, enduring intense irradiation and tidal forces, while others occupy temperate zones with milder stellar environments, potentially allowing more Earth-like oceans. This diversity calls for detailed modeling and targeted observation campaigns to classify and characterize the galactic ocean planet ensemble. Emerging datasets from ongoing and upcoming missions continue to enrich this search. NASA's Transiting Exoplanet Survey Satellite, TESS, expands the catalog of nearby, small exoplanets amenable to follow-up characterization. The James Webb Space Telescope JWST, is set to probe the atmospheres of these candidates, helping identify ocean planets by detecting water vapor signatures and assessing atmospheric compositions consistent with liquid water worlds. Additionally, advances in astrometry, direct imaging, and radial velocity techniques enhance detection of planets in wider orbits, potentially ocean-rich worlds less affected by harsh stellar radiation. Statistical surveys combined with theoretical modeling refine occurrence rates and help prioritize promising targets for habitability assessment. Collaborative projects harnessing machine learning and big data analysis accelerate the identification of ocean planet candidates from vast astronomical datasets. These tools enable efficient sifting through spectral archives to detect subtle atmospheric signals indicative of water or cloud-covered atmospheres. Beyond individual discoveries, the broader search of ocean planets fosters cross-disciplinary investigation, integrating astrophysics, planetary science, geochemistry, and biology. It prompts fundamental questions about the formation and survival of water-rich worlds, their potential for hosting life, and their role in the cosmic context of planetary evolution. Ultimately, the search for ocean planets across the Milky Way symbolizes humanity's endeavor to contextualize our own watery Earth in a rich galactic landscape. Each new discovery not only expands our cosmic census, but also ignites the enduring hope that worlds awash in alien seas may harbor diverse chemistries, dynamic climates, and perhaps even living systems somewhere amid the stars. As we traverse the chapters of Gliese 1214b's exploration, this broader quest invites us to look beyond a single star system and embrace the vast swathes of the Milky Way as a frontier rich with uncharted oceans, silent, enigmatic, and waiting to be understood. The quest to detect and analyze exoplanets like Gliese 1214b has catalyzed a remarkable wave of technological innovations, driving advancements not only in telescope design and instrumentation, but also in data processing, observation techniques, and theoretical modeling. These innovations underpin our ability to identify ever smaller, more distant, and more complex worlds, turning mere specks of light into scientifically rich subjects of study and advancing the frontier of cosmic exploration. One of the foundational breakthroughs enabling detection of super-Earths and ocean planets was the refinement of the transit photometry method. High-precision space telescopes such as NASA's Kepler and TESS were designed with sensitive detectors capable of recording minuscule variations in stellar brightness caused by tiny planets crossing their host stars. These missions pushed photometric precision to the level of parts per million, crucial for identifying super-Earths that produce shallow transit signals. The monitoring of thousands of stars simultaneously combined with long-duration observations allowed the compilation of robust exoplanet catalogs, revealing the prevalence of small, water-rich world candidates. Complementing transit photometry, radial velocity techniques have undergone dramatic improvements. Ultra-stable spectrographs like HARPS, High-Accuracy Radial Velocity Planet Searcher, and its successors operate with extreme wavelength precision, detecting stellar motion induced by planets with masses even just a few times that of Earth. These instruments require sophisticated calibration systems, such as laser frequency combs, and rigorous environmental control to minimize instrumental noise, enabling measurements with precision of centimeters per second. Adaptive optics technology has enhanced the resolution of ground-based telescopes, allowing the correction of atmospheric distortions in real time. This improvement has expanded direct imaging capabilities, making it feasible to resolve exoplanets closer to bright stars and to collect better spectral information. Coupled with coronagraphs and starshades, devices that block out starlight to reveal faint planetary companions, these technologies are essential for future efforts to image ocean planets directly. In the realm of atmospheric characterization, instruments have evolved to combine multi-wavelength spectroscopy with high temporal resolution to capture transit spectra and secondary eclipses. Space-based platforms like the Hubble Space Telescope pioneered these observations, and future telescopes such as the James Webb Space Telescope employ advanced infrared detectors with vastly broader spectral coverage and sensitivity, critical for penetrating atmospheric clouds and detecting chemical fingerprints. Data analysis techniques have been revolutionized with the application of machine learning and sophisticated statistical models. These approaches aid in disentangling planetary signals from stellar variability, instrumental noise, and background cosmic activity. Atmospheric retrieval algorithms use Bayesian inference and nested sampling methods to explore parameter spaces effectively, reconstructing probable atmospheric compositions and temperature structures from limited spectral data. Laboratory astrophysics and quantum chemical calculations complement observational innovations by providing critical molecular opacity databases, reaction rate coefficients, and spectral line lists under exotic temperature and pressure conditions. These databases are indispensable for accurate spectral modeling, the key to interpreting atmospheric data of ocean planets. Interdisciplinary collaborations have accelerated the pace of technological development. Teams comprising astronomers, engineers, chemists, and computer scientists innovate holistically, designing instruments and analytical tools tailored to the challenges posed by distant, hazy, or cloud-covered planets like Gliese 2114b. The miniaturization and deployment of small satellites and CubeSats offer new pathways for dedicated exoplanet observation missions at reduced cost, enabling targeted studies of bright nearby stars likely hosting super-Earths and ocean worlds. In summary, technological innovations in exoplanet detection and analysis encompass a spectrum of advances, from precision photometric detectors and ultra-stable spectrographs to adaptive optics, high-fidelity modeling, and machine learning algorithms. These tools have transformed our approach to discerning the characteristics of planets like Gliese 1214b, surmounting challenges of distance, faint signals, and atmospheric complexity. They empower humanity's quest to uncover the diverse array of alien worlds bathing in distant starlight, broadening our cosmic perspective and edging ever closer to realizing one of our deepest aspirations: to find another watery haven among the stars. Gliese 1214b captivates our imagination for reasons that transcend its scientific significance, weaving a tapestry of wonder, mystery, and profound questions about our place in the cosmos. It stands at the crossroads of the known and the unknown, a distant world that embodies both the promise of discovery and the tantalizing puzzle of what alien planets might truly be like. At its core, Gliese 1214b represents one of the first compelling hints of a new class of planets, ocean worlds that challenge our familiar categories of planet types. Unlike the rocky terrestrial planets of the inner solar system or the gas giants that dominate further out, Gliese 1214b sits somewhere in between. This intermediate nature strikes a chord in our collective curiosity. It forces us to reconsider planetary classifications and imagine environments where oceans might envelop entire planetary surfaces, vastly more extensive and alien than any on Earth. The planet's proximity to Earth, just 48 light-years away, makes it one of the closest examples of a super-Earth, a size range that Earth-sized planets' orbits around red dwarfs often inhabit. This relatively close neighborhood puts Gliese 1214b within reach of current and near-future observational technology, fueling optimism that we might soon unlock its secrets in detail. The possibility that we can study such a world's atmosphere, surface conditions, and perhaps even signs of life creates an irresistible allure. Gliese 1214b invites imagination by invoking vivid, if speculative, images. Endless alien oceans under skies of unfamiliar hues, extreme pressures and temperatures fostering exotic ice layers beneath superficial seas, and atmospheric dynamics so different from our familiar weather systems that they boggle the mind. It tantalizes us with the possibility that, despite its otherworldly nature, it might harbor the essential ingredients for life, or at least environments where strange prebiotic chemistry could unfold. Moreover, the enigmatic atmosphere, cloudy, hazy, and elusive in its spectral signature, adds an aura of secrecy and challenge. Unlike many exoplanets with clear spectral fingerprints, Gliese 1214b remains partly hidden behind veils of uncertainty. This scientific intrigue makes it a focus of intense observation and modeling efforts, capturing the imagination of researchers and enthusiasts alike who are drawn to the challenge of unveiling its true nature. The drama of the planet's close orbit around a small, long-lived red dwarf, leading to tidal locking and extreme environmental conditions, further frames Gliese 1214b as a stage for cosmic extremes and adaptations. How life or complex chemistry might survive such contrasts becomes an inspiring subject of speculation and study, expanding our horizons about the resilience and diversity of life in the universe. Beyond the scientific sphere, Gliese 1214b resonates culturally and philosophically. It symbolizes the eternal human drive to explore the unknown, to seek companionship in the vast darkness, and to envision the variety of habitable niches the universe might contain. It evokes questions about uniqueness, destiny, and the universality of water, the liquid of life, as a cosmic theme. In essence, Gliese 1214b captures our imagination because it is a bridge, a nearby alien world poised on the edge of our current understanding that promises to reveal completely new planetary phenomena. It challenges us to expand our scientific imagination, deepens our sense of cosmic connection, and fuels the enduring narrative of exploration that defines humanity's relationship with the stars. The notion of visiting or studying Gliese 1214b up close tantalizes the human imagination, inviting dreams of interstellar voyages and probes that might one day uncover firsthand the secrets of distant ocean worlds. Yet, anchored in the practicalities of technology, physics, and the vastness of space, this dream faces formidable dilemmas that challenge our current capabilities and prompt reflection on the future trajectory of space exploration. At approximately 48 light-years away from Earth, Gliese 1214b lies well beyond the reach of any spacecraft technology currently imaginable. Even at the speed of the fastest human-made objects, which achieve only a tiny fraction of the speed of light, the journey would span tens of thousands of years. This immense distance underscores the profound challenge posed by the cosmic scale and necessitates revolutionary propulsion technologies to even contemplate crewed or robotic missions in any feasible time frame. Current propulsion methods, chemical rockets, ion drives, or even solar sails, fall dramatically short for such interstellar travel. Concepts such as nuclear fusion propulsion, antimatter engines, or laser-driven light sails have been proposed and are under theoretical or experimental consideration. Missions like Breakthrough Starshot envision ultra-light probes propelled to a significant fraction of light speed using powerful Earth-based lasers, potentially reaching nearby star systems within decades. Yet such projects remain in early developmental stages and face numerous engineering, economic, and technological hurdles before becoming operational. Beyond propulsion, the challenges of communication and data transmission over tens of light-years are immense. A probe visiting Gliese 1214b would face enormous delays in sending information back to Earth, light itself takes 48 years for a one-way trip, requiring autonomous systems capable of independent operation, decision-making, and data processing. Additionally, energy requirements for onboard instruments, navigation, and survivability in harsh interstellar space environments add layers of complexity. Even if direct visitation remains a distant prospect, advancing remote study techniques offers compelling alternatives. Space telescopes equipped with advanced coronagraphs and star shades aim to directly image exoplanets by blocking their parent star's overwhelming light, enabling detailed spectroscopic studies of their atmospheres and surfaces. Missions like the James Webb Space Telescope and future observatories plan to characterize Gliese 1214b's atmosphere, potentially revealing water vapor, clouds, and chemical markers indicative of oceans and habitability. Robotic probes sent to our own solar system's ocean-bearing moons, Europa, Enceladus, Titan, will help hone technologies and methodologies suited for watery worlds, laying groundwork for interpreting observations from distant exoplanets. Such comparative planetary science will deepen our understanding of oceanic environments in varying contexts. Philosophically and ethically, contemplating the possible encounter with alien oceans raises profound questions. Would exploring or potentially contaminating such worlds be warranted? What measures would ensure respect for unknown ecosystems, if they exist, and for the intrinsic value of these distant environments? In the foreseeable future, our greatest strides will likely emerge from telescopic and spectroscopic breakthroughs rather than physical visitation. Nonetheless, the dream of sending probes or probes-like vessels to Gliese 1214b or similar ocean planets continues to inspire scientific innovation and fuel humanity's enduring quest to reach beyond our solar neighborhood. Thus, while the dilemmas posed by distance, technology, and resources temper the immediacy of close-up exploration, they also stimulate visionary thinking. The interplay of dreams and dilemmas around Gliese 1214b not only embodies the challenges of interstellar exploration, but also reflects humanity's relentless curiosity, hope, and ingenuity as we seek to understand our place among the stars. Gliese 1214b stands as a remarkable symbol illuminating the extraordinary diversity of planets that populate our galaxy, revealing complexities and nuances that challenge, enrich, and expand our understanding of planetary science. Its discovery and subsequent study have not only introduced us to a new category of planets, but also offered invaluable lessons about the vast range of planetary compositions, structures, and atmospheres that exist beyond the familiar confines of our solar system. At the heart of what Gliese 1214b teaches us is the idea that the planetary family is far more variegated than the traditional binary classification of rocky terrestrial planets and gas giants. Its existence evidences the presence of intermediate-sized planets, super-Earths or mini-Neptunes, that do not neatly fit into conventional categories. These planets may possess thick atmospheres, extensive water layers, or exotic interiors comprising phases of matter unknown on Earth. Understanding such worlds demands an open, flexible taxonomy, reminding us that planetary diversity is a continuum rather than discrete boxes. The intriguing interplay of mass, radius, and density observed in Gliese 1214b has sparked the realization that planets with similar bulk properties can exhibit a variety of compositions, from predominantly rocky to heavily water-laden or enveloped in thick, volatile, rich atmospheres. This degeneracy forces scientists to refine characterization techniques and theoretical models, accounting for the complex relationships between interior structure, atmospheric composition, and external environmental influences. Gliese 1214b also highlights the importance of stellar environment in shaping planetary diversity. Orbiting a small red dwarf star, It exemplifies how stellar type, radiation output, and activity profoundly impact planetary atmospheres, potential habitability, and evolutionary history. This reinforces the conception that studying exoplanets demands a holistic approach, integrating stellar astrophysics with planetary science. The atmospheric mysteries surrounding Gliese 1214b, from its hazy, cloud-covered envelope to the elusive detection of water vapor, call attention to the challenges inherent in probing distant worlds. They underscore how diverse atmospheric compositions and cloud properties can mask or reveal planetary characteristics, and challenge us to develop more sophisticated observational tools and interpretative models. Furthermore, Gliese 1214b teaches us that extreme conditions, such as high pressures and temperatures conducive to supercritical fluids and exotic ices, are common in the universe, pushing us to broaden our assumptions about planetary physics and chemistry. It encourages multidisciplinary research spanning geology, chemistry, physics, and biology to grasp the full spectrum of planetary phenomena. In essence, Gliese 1214b's story is a vital chapter in the narrative that Earth is but one among an astonishing variety of planetary forms. It teaches us humility in our cosmic perspective, inviting curiosity and continuous inquiry into the remarkable diversity that nature manifests. This knowledge not only deepens our scientific understanding, but also enriches the philosophical and cultural dialogues about life, habitability, and humanity's place amid the multitude of worlds in the galaxy. As we move forward in exoplanet exploration, the lessons from Gliese 1214b will guide our quest, reminding us to approach the cosmos with attentive open-mindedness, eager to discover the unexpected and ready to embrace the profound diversity of planets waiting across the stars. Reflecting on our place in the cosmos through the lens of Gliese 1214b, a distant, watery exoplanet, invites profound contemplation about the universe's vastness, complexity, and the delicate conditions that foster life. This alien world, awash possibly in deep global oceans and shrouded in mysterious atmospheres, challenges us to expand our cosmic perspective beyond the familiar cradle of Earth. It underscores the remarkable variety and adaptability of planetary environments, and by extension, the possibilities for life in the galaxy. Gliese 1214b teaches us humility, illustrating that Earth, while unique to us, is part of a much broader tapestry of planetary realities. Its super-Earth status reveals worlds that do not fit neatly into our categories, neither terrestrial nor purely gaseous. The study of such planets pushes the boundaries of planetary science, compelling us to reconsider long-held assumptions about planet formation, atmospheric dynamics, and habitability. Through this reflection, we appreciate that the ingredients for hosting life, water, energy, chemical diversity, may exist under an astonishing range of conditions. Ocean planets like Gliese 1214b break the mold of classical habitability, suggesting that life's potential residences might be far more varied and widespread than previously imagined. This realization fosters a renewed sense of wonder and drives the quest for understanding life's distribution in the cosmos. Moreover, Gliese 1214b symbolizes the intersection of human curiosity, technological ingenuity, and the profound desire to explore. From the faint dips in starlight signaling its presence to sophisticated models of its atmosphere and interior, our study of this distant world embodies the collective human pursuit to connect with the universe and decipher its mysteries. In contemplating this watery exoplanet, we are reminded of both our insignificance and our significance. The insignificance in the grand cosmic scale, and the significance of being capable of such thoughtful exploration. Our efforts to understand Gliese 414b, and by extension, the myriad other worlds yet to be discovered, challenge us to embrace a broader, more inclusive view of life's possibilities and to cherish our stewardship of Earth. Ultimately, lessons drawn from Gliese 1214b enrich not only scientific knowledge, but also philosophical and existential discourse. They inspire us to ponder the profound question of whether our watery home is singular or one among many, inviting us to listen ever more intently to the subtle whispers of alien oceans, forever connecting us to the vast cosmic ocean of which we are a part.